Ladies and gentlemen, welcome to Late Night Radio with Freeman Jack. We'll be taking you into the late hours, way into the late hours, and bending your mind.
You just might be right, Mr. Just might be right,
I don't know what it is about that, why it always feels so good to play into my intro music. It's been with me for years, but it does. Good evening, ladies and gentlemen. Welcome to the Open Omniversity. At this wee small hour, we'll be presenting digital virtual holographic reality theory in a slight alteration to the scheduled broadcast. I won't be actually covering the subject live on air tonight. Unfortunately, this week has been spent in a race to Friday, and unfortunately Friday won. So I got to 8 o'clock this evening with absolutely no preparation done for a 3-hour show in however long that was, sort of 5 hours time. So what I did do instead was, rather than just throw my hands in the air in dismay and run around like a headless chicken, was I spent 3 hours assembling a 3-hour show for you. And I think in the 3 hours that I have prepared in the short time that I've had to hand, I have cobbled together a typically Omniversity linear flow from the very most basic of concepts through to the last 2 hours, which will be my online interview with Tom Campbell, the physicist who wrote the M.B.T theory, the My Big Theory of Everything, which is one of the primary works of holographic reality theory. I might as well point out at this juncture that there'll be additions from myself. I present see you later, Gerald. I present my early version of my numerical flux theory, which to my mind actually extends Tom's work to some degree. There is some coverage of it in the plenum theory part of the M.B.T series, the My Big Toe series of books. But I think that even with the coverage that it receives in the M.B.T series, I think that my summation probably does it much greater service than the 50 or so pages that were dedicated to it in that series. Funnily enough, the interview with Tom has often been reported back to me by his, I don't know whether you'd call them fans, supporters, adherents, that despite having sat through all of Tom's sort of many sort of 18, 20 hour seminars that he has online, that short 3-hour broadcast had actually done more to inform them on holographic reality theory than all of the sort of Tom's solo seminar work. I find this as well. It's a lot easier confining subjects when you're a guest on with somebody else, rather than just simply having to present the ideas sort of cold at a mic. Anyway, we're going to kick off with the most basic of basics, and for that I bring you possibly one of the greatest educators ever to have taught the sciences. Now, this will be coming from an absolutely strict SI model standpoint. This is Walter Lewin from 2002. He was a physics PhD. He was a part of the faculty at MIT. If you Google YouTube Walter Lewin's Tears, you'll see the acclaim that he received to his retirement seminar that he gave, which would normally be given to a class of 15 or 20 students, and instead was given to an entirely packed lecture hall with every single academic and interested party crammed in there, and he had a sort of a multi-minute standing ovation as he walks onto the lecture stand to give his last ever lecture. And it's just he basically breaks down. And I must direct anybody to if you go to the Omniversity YouTube channel, you'll find, I think, about a 60-hour playlist of Walter Lewin's work, and as much as I in my personal work, do a lot to debunk and demystify the SI model. I think that it still needs to be taught pretty much as is, because again, this is a scalar function, and that none of these models are necessarily entirely without merit. It's just that because they don't explain everything, they need modifying or lowering in their sort of order of importance. But anyway, here's the basics of the double slit experiment. Now, bear in mind this is being given to an MIT physics degree course class. So this is essentially how physicists, or future physicists, would be taught this subject. So this is very much the SI model, and also quite a detailed model of the double slit experiment, which is absolutely key to understanding holographic reality theory, as you'll see later in the broadcast. And obviously this is a classroom demonstration, so it is rather visual, but I'm sure that you'll get the idea of roughly what's being spoken about. If you need to, again, Google images, double slit experiment, you'll see images there that will illustrate exactly what's being spoken about on all of these audios. Okay, we'll run with this one for now.
The experiment that I'm going to show you has a separation of the slits, which is 1/4 millimeter. My wavelength is 633 nanometers, which is very much the same, and the distance to the screen is about 5 meters. And so the way that we have this arranged is that the two slits, they are vertical, they are like this, and so this separation is 1.4 millimeter, and then we put over there a laser beam, and then the result is what you're going to see there. And so I now have to think about, this is where it is. You're going to see it there, and in order for you to see it, I have to make it completely dark. When you look here on the screen, you will see areas which are distinctly dark, and you see areas whereby you see the light. In other words, you see the pattern that we just calculated. You see constructive interference and you see destructive interference. And you're looking here at an experiment that is historically of great importance. It is one of the most mysterious and puzzling issues in all of physics. This interference pattern, which was first shown by Young in 1801, is clearly convincing evidence that light is a wave phenomenon. However, 20th century physics has shown that light comes in the form of individual photons with well-defined energies, and photons can behave like bullets. They have momentum, they produce radiation pressure, and they can be localized in space. We can detect individual photons in a way that we detect individual tomatoes. Photons behave like particles. However, the interference pattern that you are staring at on that screen can only be explained if we assume that each photon went through both slits. But how on earth can one particle go through both slits? It will have to be one slit or the other. And here lies the great mystery. Light is both. It is a wave if you want it to be a wave, and it is a particle if you want it to be a particle. If you manage to determine for every photon through which of the two slits it went, and that is possible, if you do it at very low light intensity, you can really determine through which of the two slits each photon went, then you will not see any interference anymore. The pattern on the screen will be like that of the tomatoes. You get two piles. So the moment that you establish the particle character of the light by determining through which slit it went, you have destroyed its wave character. And it will not behave like a wave, it will behave like a particle. However, as long as you do not determine through which slit the photon went, Thus, as long as it remains your guess through which one it went, light will reveal to you its wave character, and you will see interference. The choice is yours, but you cannot have it both ways. And so you're looking now at something that had a huge impact on physics. Clearly, at the time that this experiment was done, it was accepted that light are waves, but we now look at it in a very different way. I want to show you a slide of this, what we call double slit interference, in white light. We did it in red light. That's the easiest, and you get very sharply defined maxima and minima. And the reason why you get them so sharply defined is because you don't have the interference of the other color. But of course, if you do it with white light, then you will see the blue light has its own spacing and the red light has its own spacing. And the net result, of course, is that you see a somewhat different pattern. And that I will show you here. I will make it a little darker for that. So the upper panel is then the double slit interference in blue light. And you see the clearly dark lines, which are the destructive interference locations. And you see, as I already indicated on the blackboard, that the separation of the red is larger, because it's wavelength dependent. And if you then do it with white light, then you see something like this. So it's more difficult to actually see the maxima and the minima. Now, what you can do with light, if you can turn light plus light into darkness, then obviously you should also be able to turn sound plus sound into silence. It's just a matter of scaling up the whole experiment. And that is what we have set up for you here. We have two loudspeakers. And so all the equations that you have here apply verbatim, except that we scale it a little bit. So our D is no longer a quarter millimeter, but our D is now 1.5 meters. So here is a source of sound, and here is a source of sound. And they are fed by the same electronics. And so the D, the separation, is 1.5 meters. And the frequency is 3,000 hertz. So we do this experiment now for sound. And so lambda is about 11.3 centimeters if you take 340 meters per second for the speed of sound. So we have, in a way, monochromatic light, monochromatic sound, more or less one wavelength. And so you can calculate what lambda divided by D is. It's about 0.075. And so you can calculate where now those surfaces are. They are really hyperboloidal surfaces. They're coming out from the center here, and they bend in your direction, where all those hyperboloidal surfaces are, where there is no sound. And then you can calculate where all those hyperboloidal surfaces are, where there is sound. Let's first calculate how many hyperboloidal surfaces there are. So in order to do that, we simply have to stick in our equation, d sine theta equals n lambda. We just put in theta is the maximum value possible, and that is 90 degrees. So you put in theta max, and that is 90 degrees, pi over 2 radians. And so when you do that, you'll find that n max, that is the highest number of n in that series 0, 1, 2, 3, 4, 5, that n max is then d divided by lambda, which in our case is about 13. It is 1 over this number. So that means there are 13 of those surfaces going in this direction, but there are also 13 going in this direction. Remember, you have plus and minus. So you really have to multiply this by 2. And so there are 26 surfaces, no more and probably no less, in this audience of constructive interference. And then there are probably also around 26 destructive interference.
Okay, that is a fabulous Waterloo. Essentially what he was describing there is the interference patterns that are caused when the beams passing through the double slit experiment, through the slits of the double slit experiment, interfere. And he also referred the light experiment over to precisely the same maths which applies for sound being passed through the same device. And what he was doing there in the mathematics there that he was describing the mathematical derivation of the hyperbolic shape of the pressure waves of the interference waves as they come through the experiment. I'm going to rattle on quickly here because otherwise we're going to run way past 4 o'clock with all of this. I've got at least 3 hours of audio to play, so every second that I speak to you, I'm afraid, is another second past 4 a.m. So I'm going to rattle through a fair pace. Next we have Tom Campbell describing exactly the same experiment, but this time instead of from the specifically SI model standpoint, he explores the theoretical possibilities of the double slit experiment and brings you what most of the sage minds, even most from the Copenhagen Agreement, had to say about the outcome of the double slit experiment and its implications. So here's Tom Campbell on the double slit experiment next.
Are simple ideas, but they're hard to grasp because they are different paradigms. You have beliefs about the nature of reality, and these aren't intellectual beliefs. These are beliefs down at the gut level, down at the blood and sinew level. This is the kind of belief. They're cultural beliefs about this being an objective reality. And things I'm going to tell you will explain to you that this is not an objective reality, and I'll try to explain how and why that works, but it's going to be hard because all of those habits of thinking are going to be there as blocks in your way. I like talking about the theory because I'm a physicist and what I do is theory. But besides that, if you understand the theory, then it's much more easy for you to understand the application. If you don't understand how it works, then working with it, learning, experimenting, and growing with it is very, very difficult if you really don't understand what's happening or why. If you know the rules to the game, you're a much better player than if you don't know the rules to the game. So that's why I like to spend a lot of the time on a basic theory to get you to understand the nature of reality and how it works. That's what happens in these little spots here where there's no light. You see, between all these spots of light, that's where they canceled each other out. And all these little spots where there are light, that's where they superimpose together. Okay, that's a diffraction pattern. Simple physics back in the late 1800s. Okay, well known. Now, everybody was pleased with that until Einstein, some 2 or 3 decades after this was well known, did some experiments that showed that light came in discrete chunks of momentum. Well, that sounds like a particle. Well, it is a particle. Call it a photon. Now, light's a particle. Well, they said, if light's a particle, how do we get this diffraction pattern? Because we know particles act like this, right? Light goes through the slit. If it's a particle, it has to travel in a straight line unless acted on by an exterior force. It's Newton's second law or something like that. Okay? So we get a straight line and a spot of light, straight line, a spot of light if it's a particle. But yet light was doing this. Big mystery. So they wanted to solve this mystery by doing this experiment and firing one photon at a time toward those 2 slits. Just one particle at a time, instead of billions of particles at a time. And when they did that, they fired one particle at a time at these slits, and of course they had to keep doing one particle, another part, so they sent really tens of thousands of particles all together, but just one at a time. And when they did that, they expected they would get this, because after all, that's a particle. What they got was this. And I should also tell you that this experiment doesn't just work with light. It works as well with electrons, hydrogen atoms, and the biggest thing they've thrown through there is a buckyball. That's a 60 carbon atoms tied together in a shape like a soccer ball. It's huge and massive, compared to a photon. And they send buckyballs through there, and they do the same thing. When you send a buckyball at this, it turns into a diffraction pattern. Okay, so it's not just magic little photons that are massless particles that always go to speed of light, so they're kind of different, but anything will work. Okay, and in fact, you could throw a toaster oven at it and it would work if you could scale the experiment enough so that the uncertainty of the trajectory of the toaster oven was like the uncertainty of these photons and buckyballs, you see. So it's impractical to do the experiment for things that are too big. Doing the buckyballs was hard enough because it was so big. They had the physical experiment gets more and more difficult the bigger the particle gets. But it's a general principle that if you could throw a toaster oven at that, and if you could do the experiment, the toaster oven, there'd be a bunch of toaster ovens there, and a few toaster ovens there, and a few toaster ovens there, and none of them in between. Because the toaster ovens would go through both slits, interfere with themselves, and then recreate over on the other side. Strange, isn't it? That was the problem. Now, they thought, well, there's something funny going on at this slit. Something about going through this slit that we don't know about because we're sending one particle and we're getting a distribution that's a diffraction pattern, and that's just not right. It doesn't make sense. So let's measure what's going on at the slit. And these little red spots are detectors. They're just going to detect whenever a photon or an electron or a buckyball goes through the slit. They're just going to send a little signal and say, okay, one went through this slit. And when they detected what slit the particles went through, they got this result. Particles. Turn the detectors off. Oh, they got this diffraction pattern. Well, that's clear then. It's the detection's doing something to it. Well, that didn't turn out to be true because they could leave the detectors on detecting and just not collect any data, or collect the data and then erase it, and they got the diffraction pattern. You see? So now everybody's head was being scratched, right? This doesn't make sense. And that's why this double slit experiment is such a big deal, and that's why everybody, does it all over the world, because what it tells you is that our reality is not objective. We don't live in a Newtonian objective reality. Our causality is not objective. Okay, the next slide will tell us how they fixed the problem. They fixed the problem by saying that a particle is not a particle. There are no really massy particles out there that we can't see them. They're just probability distributions. And I don't mean by that, let's say that's a probability distribution in location of the particle. And that doesn't mean that it's out there somewhere as a particle and we just don't know where, and that's the probability distribution. It means that there is no particle. The particle itself is just represented by a probability distribution. Okay, now the reason that worked and got them out of the trouble is because part of the probability could go through that slit, and part of the probability could go through that slit, and the probability could combine with itself like a wave, and it could make a diffraction pattern. And then here, this little curvy wave that you can't see anymore that goes here, you can see it down here with the two humps, that became the probability distribution of the results. Okay. And that solved their problem because now they could explain the experiment, but it created a problem because now they said that particles aren't particles, they're probability distributions. So that was the solution. And the way the language went, they said when you made the measurement, you collapsed the wave function. This was a probability wave, and it had a wave function. It was this mathematical representation. When you made the measurement, here at these detectors, you made the measurement, you collapsed the wave function to a physical particle. Before that, it was just probability. Once you get a physical particle, then the physical particle has to act like a physical particle from then on. Now, some people said, well, I just can't believe that, measuring that particle creates the particle out of probability. There's something else going on there. And they thought, well, maybe it's when you measure it, you interfere with it. It's somehow that measurement process interferes with that particle and changes it somehow. But, of course, like I say, they left the detectors on, detecting. They just didn't collect the data, and they got the diffraction pattern. So that theory went out the window. That couldn't be the truth. But because that was the only thing they had. A lot of people clung to that anyway and believed it was true because they wanted it to be true, because that get them back into an objective reality. But it's not true. It's true that when you make a measurement, you get a particle, but it's not making the measurement. If you read this in the literature, you'll hear people talk about the measurement problem. The measurement problem is that it takes a measurement to make a particle out of probability, and that's too weird for people to accept. That's the measurement problem in physics. But it's not true that a measurement creates the problem. You also will hear that consciousness creates the particle. It's the conscious observer. It's the act of a consciousness observing the particle that makes it collapse its wave function down to a particle. That's not true either, although it does take a consciousness to make a measurement. So they're related. What it is it's about the information. If the information exists in this reality to show that it was a particle, in other words, a particle went through the slit, then it has to act like a particle. If there is no information in this reality to determine that it's a particle, then it acts like a wave. So the key thing is information. Okay? Well, this is reality is based on information. That's at the core of our reality, and that's what this says. Reality is merely an illusion. It's clear that the space of physics is not, in the last analysis, anything given in nature, independent of human thought. It's a function of our conceptual scheme. Space is a function of mind. And then at the end, Albert Einstein, after he worked the last 25 to 30 years of his life trying to come up with a unified field theory little toe, and didn't succeed, a letter to one of his co-workers. One has to find the possibility to avoid the continuum together with space and time altogether, but I have not the slightest idea what kind of elementary concepts could be used in such a theory. You see, they knew that the time of Newton was finally over, but they just really didn't know what to do with it. Because just knowing the fact from an experiment isn't enough. You have to have an explanation. You have to be able to relate it to the world before it's useful. Okay, the next one is Wigner. It will remain remarkable in whatever way our future concepts may develop that every study of the external world led to the scientific conclusion that the content of consciousness is the ultimate universal reality. Max Planck. Science cannot solve the ultimate mystery of nature because in the last analysis, we ourselves are part of the mystery we're trying to solve. See, that's like Einstein saying the space of physics is a function of our conceptual scheme. What's out here, our reality, is somehow entangled with what's in here, is what they're saying. All right. Okay, now we're going to have one from Niels Bohr. Bohr said, the common sense view of the world in terms of objects that really exist out there, independently of our observations, totally collapses in the face of the quantum factor. He meant in the face of quantum mechanics, new knowledge that they just had. Also from Niels Bohr, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet.
If quantum physics hasn't shocked you profoundly, you haven't understood it yet. Yeah, never a truer word said. That was Tom Campbell there discussing the implications of the double slit experiment. But I'd like to... I'm going to have to rattle on quickly here because I really don't want to extend too far beyond 4 a.m. I thought I'd arranged the most synchronous sequence of threes, having spent 3 hours preparing tonight's show for a 3-hour show. And when I stacked all of the audio that I'd slash edited into the player, its runtime was 3 hours, which appears to be a kind of recurrent theme in the Omniversity recently. But anyway, I'm going to move on quickly to an additional evidence, should we call it, of the holographic reality mainframe. And this is Jim Gates giving a rather nervous dissertation of his work to the Isaac Asimov Foundation lecture of 2011. If you want to go and YouTube that, it's an interesting lecture. This is a few minutes sequence from that where he's discussing his discoveries that he describes that he's named adinkras, and if this doesn't blow your socks off, then you need to adjust your heads.
No, I'm for the humility of the humanity. You know, like, yes, we're really smart, but to have the notion that we can find not just all the laws that exist in this universe, but also the laws that define the laws in all possible universes, and hence understand this one in particular, it's quite a, which doesn't mean I'm a pessimist. I think we should go there. We should totally try. But we should keep in mind that everything should, in the end, be grounded in what we can measure of reality.
But can I just say, Marcelo, that we have had incredibly successful examples of unification. Obviously, certainly, our understanding of matter is more or less unified in an incredibly successful model where we understand that light isn't different from electromagnetism isn't different from weak forces or strong forces. Where do you draw the line? I mean, would you have drawn the line before that great success? Would you have said, we have we shouldn't be thinking about unification with matter, we'll never get there, and it's just too much to expect?
In other words, Marcelo, 100 years ago, what would you have been saying?
I would have been saying that the unification of electricity and magnetism is not perfect, only in empty space. And that is true. If you look at the sorry about this, guys. If you look at the Maxwell's equations that basically describe how electromagnetic waves propagate in space, they are beautifully perfect, symmetric, whenever you don't have any sources of electricity and magnetism. If you look at, sources, they're not perfect anymore. And just to make a comment about this, yes, we have unified, and I think the tendency of unification, of simplifying our knowledge of nature is absolutely key. That's what we all want to do. That's what we'd like to do. And in fact, the standard model, which is what Jana is talking about, is a magnificent achievement in which we can describe everything that we know of particles, in terms of 12 particles, and that's just beautiful. However, it's not a pure unification in the spirit that, say, superstring theory would like it to be, because each one of the forces, electromagnetism, strong and the weak interactions, keep their imprint in the theory. And what we really want in the so-called grand unified theory or gut theory is that these three things become one. And the standard model certainly does not do that. It's really bringing them together in a sort of a patchwork way. And that is, in fact, one of the reasons why we want to go beyond that. That's one of the motivations for string theory.
Jim, have you gone beyond that?
How about Brian?
Well, it's been very interesting sitting on the stage and listening to my colleagues. But I am far from experimental physicists, as you can imagine. But this is why experimental...
Which means you're a theorist.
Mm-hmm.
Yes.
Something like that.
Yeah, okay. It's code for I'm a theorist.
I'm a theorist, exactly. But my point is that it is always the case that it is our experimental colleagues that prevent us from forming a religion, because it is always grounded in what they can measure, as Marcello keeps coming back to. And so although people can express either enthusiasm or dismay about where we are at a given point in time, I think that we need to be a little bit more humble and to understand that the process that we engage in is a constant flight from fantasy about what we would want to happen, and we query nature for that, and that query goes through experiment. So although this has probably been very entertaining for my audience here, I think that at the end of the day, we have to keep grounded in it's got to be about things that affect your lives, and those things are measurable things.
So where has this pursuit taken you?
Oh, my God.
Where have you landed?
Why would you ask that?
I'm asking that here and now. It's New York City. It's March 7th.
Well, partly it's taken to these very strange images that are behind your head right now. These are pictures of equations. I've been, for the last 15 years, trying to answer the kinds of questions that my colleagues here have been raising. And what I've come to understand is that there are these incredible pictures that contain all the information of a set of equations that are related to string theory. And it's even more bizarre than that, because when you then try to understand these pictures, you find out that buried in them are computer codes, just like the type that you find in a browser when you go surf the web. And so I'm left with the puzzle of trying to figure out whether I live in the matrix or not.
Wait, you're blowing my mind at this moment. So you're saying, are you saying your attempt to understand the fundamental operations of nature leads you to a set of equations that are indistinguishable from the equations that drive search engines and browsers on our computers?
That is correct. So,
wait. I have to just be silent for a minute here. So you're saying as you dig deeper, you find computer code writ in the fabric of the cosmos.
Into the equations that we want to use to describe the cosmos, yes.
Computer code.
Computer code, strings of bits of ones and zeros.
It's not just sort of resembles computer code. You're saying it is computer code.
It's not even just is computer code. It's a special kind of computer code that was invented by a scientist named Claude Shannon in the 1940s. That's what we find very, very deeply inside the equations that occur in string theory and in general in systems that we say are supersymmetric.
Okay.
Time to go home, I think. Where are we going to go? So are you saying we are all just, there's some entity that programmed the universe and we're just expressions of their code?
Well, I didn't say that. Some of those
like the Matrix? That's what you said.
Some of those codes are showing on the screen behind you right now. They don't look like codes, but these pictures, which we call adinkras, are graphical representations of sets of equations that are based on codes. So this is, in fact, to answer your question more directly, I have in my life come to a very strange place because I never expected that the movie The Matrix might be an accurate representation of the place in which I live.
Jim, may I give you an argument that we don't live in the Matrix?
Please. Yeah.
A very simple argument.
Give me one now, quick.
A very simple argument. There's a property that the real world right down here has that no mathematical equation has, that no solution of an equation has, that no abstract object has. Here in the real world, it is always some moment, which is one of a series of passing moments. And a mathematical equation doesn't have a flow of time in it. It just is.
No,
and this means...
But Lee...
Wait, let him finish. Wait, I need him here and now.
And honestly, they don't let Jim Gates answer. They allow that half-wit that follows him onto the microphone on the stage to just completely dismiss everything that he said with an utter load of twaddle. And what he's actually saying there is what he's found in the mathematics of string fit theory is essentially strings of ones and zeros that are not just random strings of ones and zeros. They're a specific type of binary, and the type of binary that Google uses every time you put a search term into it. So a little support, shall we say, for the holographic reality theory model. Alright, going to rattle on again. We're going to take it even further now into extended mind. Again, I think that Rupert Sheldrake is an admirable scientist for working on the subjects that he has for as long as he has and with such dedication. I would dearly love to have him join us on the Omniversity. I will be back in touch with him. I have been in touch with him in the past. However, I suspect that his morphic field theory with which he supports most of his conclusions through, as he does in this piece here, I feel is lacking somewhat. It's an elegant solution to many biological conundrums, but is far from perfect. However, this is research-based empirical science that he's actually giving you here, and this is from his Google talk called The Extended Mind. It's only a very short section. He's got 12 minutes of it here.
I'm talking about the extended mind, the mind beyond the brain. And I'm going to start with a few reflections on the nature of consciousness. We don't know how consciousness works or what it does. This is one of the things which in science is sometimes called the hard problem, because there's no known obvious reason why we should be conscious at all, or exactly how the mind works. And consciousness studies is one of the most exciting frontier areas of science today. What I'm going to suggest is that our minds are field-like, that they're not confined to the inside of the head. They spread out into the environment around us. And because our minds are extended beyond our brains, they can have effects at a distance, which are surprising from the conventional point of view, and help to make sense of a range of controversial phenomena like telepathy. So the first point is that the question of where is the mind located. I'm suggesting that minds are field-like and spread out beyond brains in a similar way to the way that magnetic fields spread out beyond magnets, cell phone fields spread out beyond cell phones, and the Earth's gravitational field stretches out far beyond the Earth. These fields are within and around the material systems they organize. And I think the same is true of our brains. The place where this becomes easiest to understand is in terms of vision and the question of how vision works. Most people think they know how vision works, and science has told us a great deal about it. And what we know is that when you see me standing here now, for example, light is reflected from me, goes through the electromagnetic field, inverted images appear on your retinas, changes happen in the cone cells, and then impulses travel up the optic nerves and various bits of your brain become active. That's what happens during the physical side of perception. There are two problems here. First of all, there's no explanation in this as to why you should be conscious at all. That's simply not explained by describing what happens in the nervous system. And the second problem is that, according to the standard view, all this is supposed to be happening inside your brain. If the mind is nothing but the brain, which is the usual assumption within the academic and medical worlds, mental activity is nothing but brain activity, everything you're seeing is inside your head. Somehow, miraculously, in an unexplained way, changes in your nervous cells lead to a kind of virtual reality display inside your head by which you see what's going on in the world. So right now, for example, somewhere inside your head, there's a little virtual Rupert somewhere in your brain, and you think it's out here as I'm standing here talking. If you look at the sky you're seeing is an image of the sky inside your head, so your skull must be beyond the sky. A recent paper in a leading consciousness journal was called, "Is Your Skull Beyond the Sky?" Because if the sky you see is inside your head, the skull must be beyond the sky. The answer of the author was yes. My answer would be no. In fact, I suggest the very common sense view, a view that's so simple it's hard to grasp, that when you're seeing something, the image you're seeing is where it seems to be. Your image of me is located not inside your head, but right here. It's in your mind, produced by your mind, but it's not in your brain. It's projected out. And I'm suggesting our whole visual experience of the world is projected out to where it seems to be. Our minds are projecting out all that we see. So vision's a two-way process, light coming in and the outward projection of images. This, I suggest, happens through what I call a perceptual field, which is a kind of morphic field, another category of field that is part of a theory I've developed, which I don't have time to explain today. But it's a field phenomenon, and in a sense, your mind reaches out to touch what you're looking at. The image of what you're seeing is superimposed on what's really there. Sometimes it's not, as in a mirror reflection when you have a virtual image, or an illusion or a hallucination, but usually it is. So what I'm suggesting is that you can, by looking at things, your mind touches them. There's a sense in which you might be able to affect things just by looking at them. Is this true? Can you affect anything by looking at it? Think of another person. Can you affect another person by looking at them? Of course, if they see you looking at them, we all know you can. But what if you're looking at them from behind, through a car window, for example, no sound, no smell, they can't see you're there, they don't know you're there. Can you affect them just by looking at them? Well, most people think that that does happen. 90% of the population have had the experience of feeling that sometimes when they're being looked at from behind, they turn around, someone's looking at them. Surveys show that more women than men have had that experience. It's still a very large majority. More men than women have had the experience of looking at others and making them turn around. But most men and women have had both these experiences, and I guess most people in this room have experienced these things personally. So The sense of being stared at is a well-known phenomenon. It's found all over the world. Children know about it, adults know about it, but it's not part of the standard scientific map. You won't find any reference to it in psychology textbooks. There's virtually no research literature on this until about 15 years ago. And it's extraordinarily under-researched in spite of the fact it's very well known. The standard scientific education that most of us receive makes us think, well, this must be some kind of illusion. So probably most people in this room have been trained to dismiss the phenomenon by saying, oh, it's just a coincidence. You turn around all the time. If no one's looking at you, you forget about it. If they are, you think there's some mysterious sense involved, but it's really nothing but either coincidence or peripheral vision or something like that. That's the standard way of explaining it away. But now many experiments have been done to test whether this is real. And the simplest experiment involves people working in pairs. One sits with a blindfold with their back to another. The other person either looks or doesn't look at them in a randomized sequence, and in each trial the person has to guess if they're being looked at or not. Hundreds of thousands of these trials have been done. The overall results show a positive, very significant effect. When things are repeated over hundreds of thousands of trials with many independent replications, they become very significant, even though, as in this case, the effect is fairly small. These experiments have also been done in Amsterdam in the Science Museum in one of the largest experiments ever conducted for more than 20 years. This experiment's been running. More than 20,000 participants have taken part. The results are, again, overwhelmingly positive and significant. Rather surprisingly, this phenomenon also occurs through closed-circuit television. Various experiments have been done whereby people's skin conductance is measured with electrodes on their fingers. This measures emotional arousal. And it turns out that there's a significant change in people's emotional arousal when they're being looked at through closed-circuit television by someone on a monitor in a different room. This work's been replicated as well. One of the people who's done it, Marilyn Schlitz, is right here in the Bay Area. Indeed, she's right here in this room. So there's now a substantial body of work showing that people can tell when they're being looked at, even through closed-circuit television. This is something which has become of great interest to the security agencies, and I can't divulge exactly who or why, but I can tell you that the security forces are very interested in this question. Could a potential terrorist, for example, tell when they're being watched through closed-circuit television? The answer to that is probably yes, if they've trained their sensitivity a bit. This phenomenon is well known to security guards. Most security guards are well aware that if people are looked at from behind, they can tell when they're being looked at. Private detectives know that when they're shadowing people, when they're following them, they shouldn't stare at their back because the person's likely to turn around and catch their eye and blow their cover. People in the martial arts know about this, and there are martial arts methods for training your sensitivity to feeling people's intentions or looks from behind. And in the closed-circuit television industry, which now involves millions of CCTV cameras engaged in surveillance work, many operatives know that you can affect people by looking at them. I gave a talk about this in Washington, D.C. last year, and one of the guys in the audience told me afterwards that he was, in fact, a security guard. And when he was trained by an FBI trainer, they told him, if you see someone doing something they shouldn't do, just stare at them hard on the screen, and they'll probably stop it. And I said to him, does that work? And he said, sure, I do see it almost every day. He said, we all know this stuff. He was amazed that this is a controversial issue within the academic scientific world, because people in the security industry take this for granted. In the British Special Services, the SAS, when people are being trained how to stab others in the back, they're trained that you don't stare at the person's back before you stab them, because they're likely to feel it, turn around and shoot you. So these things are completely taken for granted, yet they're a huge scientific anomaly. It shouldn't happen if the mind's all in the brain, but if our visual activity involves the outward projection of images, and even a kind of resonant projection when you see something on a computer screen, it's not a direct effect. In that case, just seeing the image can affect the person. Something else is going on. I think our minds are, in fact, extended beyond our brains in every act of attention and perception. And this is not a new view. It's a view put forward by Plato and other Greek philosophers. It's the view of perception in most Hindu and Buddhist philosophies. It's the view taken for granted by traditional people all over the world. And it's the view taken for granted by Western children under the age of 10 or 11. Studies on children's intellectual development shows that most children assume that vision involves this outward projection. That's why Superman comics and things show rays coming out of the eyes of superheroes. It's a very popular childlike way of seeing or understanding. Piaget, the developmental psychologist who studied children's intellectual development, said that by the age of about 10 or 11, the average child learns the correct view, which is that thoughts and images are invisible things located inside the head. We've all been brought up with the correct view, in spite of the fact there's virtually no evidence for it. No one's ever seen a thought or an image inside a head. And our own experience of seeing things outside us directly contradicts this theory. So we've bought into a theory that's totally at variance with our most immediate experience. And I'm suggesting our minds reach out beyond our brains, and the sense of being stared at is one aspect of this.
I'm going to rattle through this a bit quick. That was Rupert Sheldrake with a short excerpt from The Extended Mind. I may well bring an awful lot more of Rupert Sheldrake to the Omniversity. I think that he is a gold standard scientist, has done much to extend the subject of mind science. I'm aware that I'm already overrunning by at least 11 minutes. We're probably looking at more like 15 or 20 once all the run times are up and running. So I'm actually going to step away from the mic now until gone 4 o'clock. And first of all, you have 2 introduction pieces that will run to about 10 or 15 minutes in total. These are my personal work on holographic reality theory. These are my Benificence and Obselecence work, followed by my very early numerical flux in the computational mainframe. What you'll actually hear me reading there is actually the piece that I sent to Ted Vollers, who was Tom Campbell's colleague and co-author in M.B.T. Like I say, he was so kind as to point out that effectively in my very short summation that I had broadly speaking, covered about 50 pages of the M.B.T series that covers something called the plenum theory. And when I read those 50 pages, personally, I feel that my theory is slightly more elegant than that which is presented within the M.B.T books. I don't want to do Ted or Tom a disservice. I don't think that in any way is in any way dismissive of their work. I think it's a towering work, but just in my possibly innocence, I perhaps stumbled onto a more elegant description of how the computational substrate, the computer on which this hologram is actually constructed, is made. So I'll see you after the Tom Campbell for a little outro, but here's me twice and then me interviewing Tom Campbell from 2012 for the last 2 hours. Now obviously if any of you are trying to stay up late, you will find the entire Tom Campbell audio on my Freeman Jack YouTube channel. I'll drop links into the podcast page and the YouTube upload for all of the audio that you've heard here, so you can go and review the full audios if you so wish. And the last 2 hours now from about 20 minutes time. If it's rather late and you're struggling to stay awake, you won't be missing anything if you simply visit my YouTube channel and go for the full 3-hour Tom Campbell interview. I've edited it down for 2 hours for tonight's broadcast. Anyway, here's me on Benificence and Obsolescence. There'll be a short music break after the numerical flux theory before we go into the Tom Campbell interview, just to give you all a chance for your brains to steam a little and to have a comfort break and run off to the toilet and flick the kettle on. Okay. Of Benificence and of Obsolescence. If we assume that the clockwork nature of the universe that we perceive is driven by mathematical truisms, that the perceived procession from next to now to then in a consistent line wherever we look, then it must be assumed that that linearity is contained and described by mathematics, that you can mathematically describe, like Newton did with the laws of gravity and the likes. You can mathematically predict the regularity of reality. Okay, I would go one step further than that, and I would suggest that the very nature of reality itself is mathematical. That everything that we see, all of the stuff that we see, all of the nature of reality is nothing more than the interaction of mathematical algorithms. Funny enough, somebody mentioned that perhaps when the universe was a simpler place, that we may have been able to recognise the patterns more clearly and therefore be able to affect reality more clearly. But again, this is not consistent with what I'm looking into, and what appears to be the case is in fact that the linear nature of time and that the progression and self-evolution of reality means that this quite literally is the apex moment of the time-space time frame, that it's always the apex moment. This is always the best time to have been alive. There will have always have been more faults with reality then than there is now, and there will be less faults with reality in the coming time. And the very reason for this is that in order for order to have achieved this higher level of complexity, for there to be atoms and planets and stars and people and cars and mountains and plants and birds, okay, that wouldn't, if there was no linearity, if there was no selective evolution, then that would not be the case. Okay, the very fact that we see an ordered universe, an ordered reality, an organised reality, that organisation hasn't been created by the hand of some beardy twat in a fucking cloud, right? That organisation was a very basic, predominant fact of the way that creation came about in the first place, and that creation was driven by the sea of number stringing together algorithms that became self-evolving, and having became self-evolving, they didn't self-realise, you know what I mean? We didn't become sentient because the numbers began to start churning. But what would have then happened was that the self-evolving nature of it had to have developed at some point a preference for the beneficial, and possibly even some sort of a mechanism for eroding away the detrimental. So not only did the number set, the number interaction begin to self-evolve, that it generated algebraic equations that would simply self-generate more algebraic equations. Now, if that hadn't had some sort of beneficence acquired as a nature of consistently failing, yeah, that if in the absence of beneficence, okay, in the absence of some way of encouraging, or at least keeping hold of that which is an improvement over that which is a detrimental thing, then those fractal self-evolving sequences would have simply disappeared back into the number Maya, because there wasn't any guaranteed progression built in. Eventually, through the infinity of time, they would self-collapse in effect, that they would evolve and collapse. They would be evolving and collapsing systems. So in order for us to see the level of complexity, the level of order that we see, there has to have been something in those original Big Bang mathematics. And I described the Big Bang as mathematics. The Big Bang wasn't a physical event. The Big Bang was a mathematical, it was a numerological event. And it was an inevitable consequence of the interactions of number, of the reality of number, the fact that if I'm standing here and you're standing there, I'm a person, you're another person, that makes one, that makes two. Whatever two things you bring together can be described in two. It doesn't matter what language you describe them in, it doesn't matter even if you don't have the concept of number. Number exists without the concept of it ever being thought about. So number is really the only thing that can have existed before there was anybody to think anything. So we have this evidence of beneficence being preferred over obsolescence. That obsolescence would have essentially have become obsolete. That obsolescence wouldn't have been preferred in the early mathematical algorithm, and so the imprint of that successful first algorithm would have been one with a bias towards beneficence, and that may have been all it was. Yeah, in the initial phases, that would have all it would have been needed to be. Even the physicists say that in the current model of the Big Bang, that there had to be a preference somehow for matter over antimatter, because there would have been equal amounts of both created, and had that situation have been consistent to the universe that we see now, stars would be eating each other all over the place. In fact, there would never have been any stars, because the matter and antimatter would have simply have decayed into small energetic bursts. So even the most grounded of astrophysicists will gladly tell you that there was an obvious mechanism at work that is ill understood, that meant that matter was preferred over antimatter. Okay, that the particles were preferred over antiparticles, and as a result, the observed universe has a very small amount of antimatter in it, and is largely, the observable universe is all made up of matter, although antimatter, if it exists, is out there, it's out there in very small quantities. Numerical flux and a computational mainframe. Reality is a digital matrix. This matrix is driven by mathematical logic. It is unlikely this mathematics is derived from base 10, denary, or even binary. The most elegant number system appears to be base 12. In a spherical universe, base 12 has the most concordance. As thinkers in denary, base 12 presents some difficulties to overcome, not least of which two new unique numbers with which to express the concepts of 10 and 11. In base 12, these two numbers are obsolete concepts. As thinkers in denary, base 12 presents some difficulties to overcome, not least of which two unique numbers with which to express the concepts of 10 and 11 in base 12. These two numbers are obsolete concepts in base 12. The use of an 11-beaded abacus avoids the need for this consideration. However, when thinking about the output of any calculation, base 10 thinking must be avoided. Reality is geometric. It has 3 dimensions of space and a direction of time. The initial geometric form is the triangular pyramid, the tetrahedron. It requires the fewest lines and points. Let us examine dimensions, starting with the point. Of course, the point has no area or length. It is theoretical. 2 points define a line, the first dimension. A line has length but no thickness. It is theoretical. 3 points describe a triangle, the first 2-dimensional object. It has length and width but no height. It is theoretical. 4 points make a tetrahedron, a triangular pyramid, the first platonic solid, the primary 3D object. Reality at last. Time can be thought of as a change of state or rotation through the other 3 dimensions. Now let us consider the topography, the shapes of surface. Largely, we only see flat surfaces, but this is a deception of scale. We live on the curving surface of a sphere. As a result, apparently vertical parallel walls of a building are in reality 2 divergent lines whose common source is the Earth's centre. Subsequently, concepts such as up and down would be more accurately described as out and in. Indeed, it is a reasonable model to use quadrants of a hemisphere as a basis of all geometric considerations. A quadrant of a hemisphere is a tetrahedron. It is therefore reasonable to model reality in a tetrahedral grid. Human mathematics is linear and largely lateral or one-dimensional. There is no reason to assume that the same is true of the mathematics of reality. Indeed, the mathematics of reality, if the mathematics of reality use the same economy of form that geometries use, then we might consider attempting to use tetrahedral maths, with each point being an input or product and each line being an algebraic equation. Any input of data at any point would simultaneously, relativistically alter the condition and product of every interconnected point. This would produce radiant waves of interpolated fields of number. It is entirely possible that we live in a polarized reality, one in which we can only observe, let's say, horizontally polarized matter. We could live in complete ignorance of anti- or vertical reality, as our senses and scientific equipment are all made of the same horizontally polarized matter. This polarization would suggest a star tetrahedral geometry. A pair of tetrahedra inserted through one another, the upper point of one extending through the base of the second. If data or energy is inserted into this symmetrical polarized system, the resultant energy field would be a double torus with energy flowing and returning in both outward and inward streams. If extended to the subatomic realm, this might explain observations such as electrical polarity and up and down spin. If reality is digital and virtual, then its very construction must be numerical. At the atomic scale, we see a constant state of flux. I feel this is the closest direct representation of what may be happening at the numerical or computational level. Assuming that time runs more or less in a linear flow as we tend to observe it, then the evidence of some sort of expansion appears to be visible. It is my suggestion that in some primordial universe, that number and numerical interplay was all that existed. Due to the eternal churning flux of these computational numerical interactions, sequential strings of numbers would eventually occur. Initially, these sequences would be incoherent and unstable and result in no evolution. However, over eternities, successfully adaptive algebraic interactions would collapse out of the general background flux. Initially, I see these numerical sequences being most likely linear or two-dimensional. A numerical neural network Initially, I see these numerical sequences being most likely linear or two-dimensional. A neural network eventually. Initially, I see these numerical sequences being most likely linear or two-dimensional. A neural network eventually. Interconnected algebraic sequences could then, again, given time, express every possible numerical value in either linear or two-dimensional form. A calculable number of iterations would accomplish this. Having filled the available computational space, the same evolutionary pressure would eventually force a fractal Mobius pinch point, expressing all of the computational complexity of the 1 or 2D into this new third dimension, but without occupying any of its volume. I feel this is how reality came into self-realized existence without the need for deity, driven only by the fluid interactions of number and the evolutionary pressure driven only by nature's bias towards the successful and against the obsolete. This is one clear law of nature. In conclusion, reality is a novelty factory, and we are novelty factory assembly workers. Our nature is to create a lot of novelty and complexity. It strikes me that this, in and of itself, is enough.
Got no brain or thought telling folks that you suddenly gonna lame, or that the white folks have finally co-opted your game, or you really don't know. They said that about me a long time ago. If they finally start telling people that you lost your nerve, that's what they said about Johannesburg. You ain't insane. You have got a brain. You haven't gone lame. You have got your game. Remember, keep the nerve. Keep the nerve. Keep the nerve. Keep the nerve. We're talking about peace.
And it's Freeman Jack and Bitchin' Bob with the fabulous Dr. Tom Campbell, author of My Big Toe, and that's where we're going to go now. Hello, gentlemen, glad to have you back. So far, we've discussed taken a fairly ponderous introduction to Tom himself, Tom's work and history, and hopefully illustrated why this theory is important, of just exactly the magnitude of that importance. So I'd really like to give Tom the floor now, simply to give his, I suppose, 1 hour take on my big theory of everything.
Well, we'll maybe do it in pieces. When you say 1 hour take, everybody just got up to do something else.
Oh, Tom, you'd be surprised. My listeners are entirely used to content of this sort of nature, and I can assure you that since we were about to come on air, the chat box on TNS filled up, and the chat box is always an exponential reflection of the listenership. So the fact that it was being publicised that you were coming on, substantially, probably 25% increase in listenership just a few minutes before you came on air. So really, sir, please don't think that you need to hide your light under a bushel. We have a very adult listenership and a very enlightened one.
Good. Yeah. Now, taking an hour to explain the basics of the theory, of course, is hard. When I stand up at my workshops, it takes a day. You know, I do theory in about 7 or 8 hours. So this will be a little on the short side, in as much as I can give you the kind of a series of bottom lines, and then you can maybe ask me some more questions if you think there's something that's particularly hard to understand. But when you see the whole thing, when you actually get it, it's really very simple. You said that when we first started this. It is very simple, but you have at least 2 or more paradigms to leap to get by, and those are difficult. They're hard to do. Your habits of thinking just keep pulling you back into kind of the same traps again, and it's kind of difficult to get there. And the first paradigm that you have to jump is the idea that reality is information. Okay, reality is information. Now, to help people get that, I make a little analysis of their senses. You know, your reality, what you think of as reality, is what we call physical reality, and all that is information. Here's how. When you look, let's say, take the eye sense, take the sight. When you look, you're getting light that creates a little pulse of neurons. You know, you get a little electrical signal at the retina, where the lens focuses the light on the retina. The light hits light-sensitive cells, and the light-sensitive cells create a little charge. Those charges then go down the nervous system. They stimulate neurons. The neurons form patterns, and so on. So basically, those neurons, those light signals, those little bumps of electricity created by the light, that's just information. When you smell or hear or touch anything, it's just data. Okay, data is information. Then you interpret that information, and you interpret all those little electrical signals and neuron patterns. You interpret as this reality. Okay, so that's what this reality is. It's just information. And an interesting thing is that information is not physical. You can't weigh information. You know, how heavy is information? How much space does information take up? What's the volume that holds information. Well, there is no space or volume, and that means it's non-physical. Information is the content. Now, of course, you can weigh a book, and it takes up space, but the book is not information. The paper is the media. Okay, the ink provides the code symbols, but the information requires interpretation of those symbols into meaning, and that can only be done by a consciousness. You take a picture of the book, take a picture of the page of the book, and the camera doesn't get any information. It's only a consciousness that has to decode the code symbols written on the media. Then the information's created in that consciousness, in the mind of that observer. So information exists only in consciousness. So what is this reality? It's just information. Where does this information exist? In consciousness, you see? So that's kind of a way of helping you see that this idea that the reality is information is not all that far-fetched. Now you get down to the quantum mechanics level, and the people in quantum mechanics have known a long time that reality is information. It has to do about their experiments revolve around information. Information is sometimes called measurement. And they also know that the fundamentals of reality is information. Many of them struggle to somehow pin that structure onto objective physical reality, but it doesn't stick. And that's why they think quantum mechanics will never be understood, because there's the way it acts, which is as information and non-physical, and the way they believe that it ought to be, which is objective and physical, are at odds with each other. And that's the quantum mechanics is weird science problem. So first thing, we have reality's information. Second thing is that this information exists in an information field, and we can model this information field as being digital. Why? Because, digital is the simplest way to generally portray information, and binary is the simplest way to generally portray digits, bits, if you will. Now, it's not the only way. You don't have to work in binary, and things can be, you can have analog information, but it's very limited. If you want an unlimited resource, then you end up with a digital information field. And let's call digital information field a computer. That's what computers are. They're kind of digital. The computer, it's hardware, it's hard drives, it's memory, it's processing, all works inside of a digital information field. So now we're beginning to see that reality, our reality, kind of looks like a computer, and that this is a virtual reality. Now, we all know about virtual reality. We have virtual reality games. Two I know about are the two that my children played when they were young, and one of them is World of Warcraft, and the other is The Sims. Right? The boys play World of Warcraft, the girls play The Sims. That's generally the way that works. So you have these virtual realities, and they are generated as information inside of a digital information system. Okay, so all those the pixels light up on your screen because of information. There's some information that tells which pixel to light up at what intensity and at what color. And all that information then creates this world on your screen. So that's a virtual reality. By virtual reality, we mean virtual as opposed to it's computed. And of course, the opposite of that, well, if it's not virtual, it's real. Well, if it's real, we think that means physical. That this physical reality is the real one, and that The Sims is the virtual one because we create it in a computer. But then it turns out we have to take one step back and realize that our reality is also virtual, and that we are created in a computer. And that just
to explain, Tom, I think a slightly clearer explanation of virtual is that the virtual realities that these characters wander around in is one that's created from the re-expression of a single algorithm to create the textures and the surfaces, rather than actually defining each point on the surface. Would that be a more specific description of virtual?
Yeah, well, there's different kinds of virtual reality, and actually, I'm getting a little, I'm going to confuse your audience. Let's put it this way. There's different ways to make a virtual reality. Now, when you make a virtual reality like The Sims, that's done with algorithms that specify the way, everything's supposed to look. Now, that means that things like grass, you don't have to plant each blade of grass. You can have, just like you say, a reoccurring algorithm, or it can just kind of look like a green carpet where you don't show individual blades of grass or individual strands of hair on furry critters. So that's a programmed virtual reality where some programmer sat down and had to create information or algorithms that created information for all the points on the map, if you will. All the points inside the virtual reality had to be generated by algorithm or by a computer programmer putting them there. Now, there are other ways to create a virtual reality that, like our virtual reality, what we call physical reality is a virtual reality, but it was created quite differently. The way it was created is it evolved. It's not a programmer that plants every blade of grass. It's an evolved reality. So you take, let's say we take a lot of energy and we confine it to a very small space, and we give it certain rules about how this energy relates, how energy transfers have to be made. So we give it the basic rule set of how it will interact, what it will do. And we put all this energy in a very tight space. Now, this is a computer simulation, right? So we're just simulating it. We can say how small the space is, how much the energy is. Those are just input values. So we make this computer program, and then when we punch the run button, we let all the logical consequences be computed based on the rule set of how this virtual reality, interacts. What are the energy exchanges between the particles or the elements in it? So they push the button, and that's what's called the big digital bang. So that in the computer, in that simulation, that ball of tight energy expands. As it expands, it cools. As it cools, one of the rules is, of course, gravitation. Chunks of it tend to coalesce. And eventually, of course, you end up with our universe, and then you end up with us on a little planet going around a star, and our own evolution locally on this planet. All you need is the right kind of amino acids, and get together, and you end up with some kind of very vague, maybe virus kind of thing, or a cell of some sort, and then the cells get together and decide to cooperate, and then you have multi-celled things, and so on up the chain. You have this reality that has evolved in this computer. All of it is just evolved in this computer. Okay, so that's the framework then for our reality. Well, then what are we? We are consciousness. We're individuated units of consciousness, and we are going to kind of play in this virtual reality, just like my daughter played in the Sims reality. We're going to go play there, and the way we do that is that we have to follow the rule set for this reality. We can't do things that the characters, can't do, and they're constrained by this evolved reality frame. So let's say in this evolved reality frame where we had the little spot of energy and it expanded, we ended up with the universe, we ended up with our planet, we ended up with human beings and all that sort of thing. And these human beings, let's say, can only jump 3 feet in the air. They can't jump 20 feet in the air. Why not? Well, according to the way they evolved, their weight, their muscle structure, and the way they're built won't allow them to jump 20 feet in the air. So this consciousness has to abide by the rule set. It can't do things that are, let's say, not supported by the results of this simulation. So if this character gets hit over the head by a crowbar by a villain and it damages his brain, oh, well, you've just created new constraints. So now that character can no longer think as well as he did before because now he has brain damage. So there's more constraints added because of the energy of the blow and how much energy it would take to crush the skull and so on. All of that just goes by the rule set. So what is this rule set? Well, it's our science. At least science has dug out, a lot of the rules. There's still some rules that it hasn't dug out yet, but it's dug out a fair number of them. And Those are the rules called physics by which our reality works. So here we are, consciousness. We're playing in this game. We're being constrained by the sets of rules, and it's a multiplayer game. So it's interactive, just like Sims and World of Warcraft. It's interactive. You have different players. You have players run with a computer, and you have other players from all over the world who have kind of paid their $10 a month and have signed on, and everybody can interact. So if another player walks in front of you, you see them walking in front of you. Why? Because it's just information. The information knows where each player is by the way the player moves and where they're located and that sort of thing. And it knows where you are, and it knows what's in your vision, and it displays that. So that's the same way it works in World of Warcraft and Sims is the way it works here. So that's the first big paradigm that's very difficult for most people to get, because at a deep level, they have learned from their culture that physical reality is real and it's solid, and they probably even believe that it's kind of all the reality there is. All reality is contained within our universe. Well, that's like saying that all the world is flat. You see, it's a mistake. It's taking something that appears that way, but really isn't. You know, the world really appeared flat, but as far as you could see, it seemed to be flat. You know, because you don't know what you can't see. But in any case, that's the first big paradigm shift. You have to understand that reality is virtual and that it's information. And science, now where's physics on this? Science has come a long way to supporting this. Every few months I hear about some other physicist someplace who kind of signs on to the virtual reality paradigm because it's just better physics. It explains things much better than the old physics, which, you know, physical reality is all there is, and it's objective.
Well, and also is riddled with paradox and nowadays a large degree of scientific dogma.
Yes, exactly.
And
so they have all these paradoxes, things that do happen that shouldn't happen, and you have a very strong science house like Princeton, who has this group of people that are kind of an offshoot of Princeton, and it's called PAIR, Princeton Engineering Anomalies Research. And for the last, 25, 30 years, they've been doing research showing how mind affects matter. They use people, they use their graduate students and so on, that have their intent focused on changing a particular thing that, according to the physics, shouldn't change. They can bias statistical distributions and that kind of thing with their intent. And this has been going on, like I say, for a long time. The scientific protocols are immaculate. They're probably 10 times more, 10 times more precise, more conscious of possible errors and conscious mistakes than general science, because they know these answers are impossible. You know, this can't happen. It's something that we don't know. So because it's doesn't have any theory to explain it, they are very, very careful about controlling their error sources and controlling the protocols. So their scientific method is probably the best and most rigorous in the business. And yet they consistently show that these things work. Now, that's one of these, conundrums. Like, how is that possible? Well, if you understand virtual reality and our reality as a simulation, and then the next step, the next paradigm is understanding that this simulation is probability based. It's not, nobody's calculating every pixel, in our reality. It's all based upon probability and statistics. And then when you understand both of those things, then suddenly what's going on at PAIR Labs is a logical conclusion. Well, of course it's that way. It has to be that way. It couldn't be any other way. So we've come to our second paradigm, that our reality is probabilistic. And the way it works, and the double slit experiment told us this. It very clearly shows us that reality is probabilistic. That's how it works, and that it's informational. But quantum mechanics has kind of gone on with the computation and denied the foundation, that it is not understandable. So let's talk about that a little bit, because I want to then get to this next paradigm about it being probabilistic. In double slit experiment, and if you want to see pictures of this rather than just listen to me talk, you should go to one of the videos on YouTube. You can either go to my channel, which is TWCJR44, that's TWCJR44, or just go to YouTube and put in Thomas Campbell, and you'll come up to the site, and you will find lots of videos, and almost any of the workshop videos will have a section on the double slit experiment, and a couple smaller videos I discuss it. And what it amounts to is that if you have a barrier with two slits in it, two holes cut in it, and if you throw a particle through one hole, you expect it to hit the background, which is on the other side of the barrier, right behind that hole. And if you throw a chunk of matter through, either one of those holes, you would expect it to land behind the hole that it went through. That's the way matter is. It's what Newton told us, that's the way matter works. And indeed, if you measure where these electrons, let's say the particle is an electron, if you measure these electrons, which hole they go through, that's exactly what you get. You get a little pile of electrons behind each slit. Now we're firing electrons at these slits one at a time. So if we measure which hole, here's this electron and went through this slit, and it ends up in a pile right behind the slit, and so on. But if you don't measure which hole they go through, you just let that electron gun just fire away, and firing one electron at a time, you end up with a diffraction pattern. They don't end up behind one slit. They end up spread in a pattern that looks like a wave pattern. So that was a big question back in the very early 1900s, is how can that happen? How can these single particles distribute themselves like a wave would distribute its energy when we're firing them one at a time, one particle at a time at these two slits? The answer to that is that the particle isn't really a particle. See, here's where they found out that their belief that an electron was a little chunk of mass with a charge, that was an inference based on their measurements, and they believed that it must be true. And then they got their comeuppance when they got to quantum mechanics, when it turned out it just was not true, that it was just a model, and it wasn't even a very good model, because it didn't explain the results that they were getting with the double slit. They realized that electron was probability. It was a probability distribution. It had a probability of being somewhere, and some of that probability went through each slit. The probability interfered with itself like a wave, and then where there was high probability, you got a particle. Sometimes it's probabilistic. Sometimes you get one at this spot, and sometimes a spot a little further over, and sometimes another spot based on probability. So they realized that particles are really probability, and that when you don't know, because they're so small, they're easy for them to get lost. You might say it's easy for us to lose track of them to where we don't know where they are, and then they're described by probability. In the larger world, that's a little harder thing to do. So this turned out, this became obvious at the level of subatomic particles and atomic particles.
And that's really the key
reality. Well,
sorry, Tom, that's the key paradox that I was just alluding to, where really to accept the modern scientific model, the paradox of the double slit experiment and its the inexplicability between the wavy particle that has to be assumed to exist for both experiments to be right is just kind of shrugged and walked away from by mainstream science at this point. It had no answer, often no answer, and literally just kind of carried on building its model on such shaky foundations.
Right. Well, they have actually no foundation at all. They just know it's a fact. And they take that fact and go off and say, well, if that's true, then what are the logical implications? And they've worked up a system of mathematics that explains what those logical implications are. And that's what quantum mechanics is. It's this mathematical formalism that computes, other than experiment says that it's a fact. But why should the world be like that? Why should reality just be probability? Well, it's just information, and it's information within a probability and statistical model in a virtual reality. So you see, it's starting to make sense, and things. The foundation under quantum mechanics then starts to firm up as, okay, we understand that. Reality is information, and it's probabilistic. Well, that's good. And it also solves the pair research lab, solves their problem as well. Mm-hmm. So now our next step on this series of paradigms that one needs to kind of crawl through in order to see this bigger picture is to realize that we as consciousness interact in this reality frame. And one of the ways we interact with it, and I guess I'll have to then backfill to make this reasonable, but one of the ways we interact with it is that our intent, the intent of consciousness in this virtual reality, actually modifies the probability of what will happen in this reality. Okay, so intent modifies the probability. So imagine you have this reality, and it's based upon probability. And you have beings that are playing in this game, and the things that happen next, okay, there may be 100 different things that could happen next. Some of them are more or less probable than the others, okay? Then a statistic, you kind of reach up into this distribution of the possible things that could happen and all the probabilities that they might happen, and you randomly pull out one, okay? And the things that are more likely to happen, of course, are more likely to happen, because that's the way, that's what it means to be a statistical distribution. So you pull out this random value, and that's what happens here. That's what you get. And then once you have it in this reality, then it has to stay. The reality has to be consistent. Otherwise, it's not a very good reality if it's not consistent. You can't have different people in the reality, seeing different things. You have to have it consistent. So that's one of the rules that we follow, that once something comes into this reality, it has to be physical. It has to abide by the rule set that creates the simulation that we call physical reality. So then that means when they measure that electron at that slit, the measurement is the act where you reach into that probability distribution and pull out an answer. You see, we don't know. It's just probability. Where is it? So we measure, and we make the measurement. We create information here in this physical reality, and we say the particle is right there at that slit. It's just going through this slit. That's information. Now that is what the physicists would say collapses the wave function, and this is a probability wave function, collapses the probability wave function to a physical particle. From then on, it can't do anything but act like a physical particle. It has to travel in a straight line, until it hits the screen behind it. So it's the act of measurement that, if you will, kind of creates the particle there, and then it has to act like a particle afterwards. That in physics is called the measurement problem. The measurement problem is a problem because it shouldn't work that way. You shouldn't create particles by measuring.
By measure.
You see? So that is why they call it the measurement problem, because it's another one of those impossible things that don't make sense. It does make sense very easily if you see yourself in a virtual reality that's run by probability and statistics. Now, the things that they do at Pair Lab that we've mentioned, they use their intent to modify those probabilities. That's the part that they have shown to be, a fact. They can use their intent. They set up things that produce random distributions, and then somebody's intent, like a radioactive decay. So you have a radioactive source, and it'll decay in some random direction, and then you have Geiger counters that count. Did it decay into this Geiger counter, into that Geiger counter? It's exactly the same probability that it'll decay into either, because it can decay in any direction. So you just have counts on these two different Geiger counters. And after a while, you'll have millions and millions of counts if you let it go long enough, and you would expect them both to be about the same. Well, if one was, a couple more than the other, then you kind of expect that, because over time, they would tend to be the same. But they let somebody, after they collect that data, or even as they collect it, they can let somebody have an intent that, say, the left Geiger counter will get more counts than the right one. The right one will get less and more in that. So it'll be traded. Some of the ones will be taken from the from the right one and put to the left one, if you will. Some of the decays. It's going to decay preferentially then in this one direction, which physics says is impossible. It's a random decay. But sure enough, they can do that. They can modify, they can get probability distributions that show a statistical significance in the inequality of the counts in the two detectors. Well, this detector now has, more. And what's the probability that it could have gotten that more just kind of by accident? And it's like, 1 in a million, 1 in 100,000 that it could have gotten that more just by accident, by random fluctuation. So they know it's a real effect. And intent, conscious intent, modifies the probabilities. And the reason for that is it's a feedback mechanism that helps us interact with this computer simulation game we call physical reality. And to understand why we would have this feedback, you have to understand now another paradigm shift, which says, what is consciousness? What is this consciousness system? And what's it doing? Why does it act like that? Well, consciousness system is a digital information system. What do digital information systems do? Well, they create and deal and move information. What is information? You go into information theory, you will see that randomness, which is all the bits are just random, has no information. If you take those bits and put them in some sort of a pattern, that's called information. You see, because no longer it's random, it's in a pattern. So what information systems do is that they decrease their entropy. Entropy is a measurement of order. So you take all the bits and they're random, there is no order. That's very high entropy. If you take those bits and arrange them in some sort of a pattern, like take those bits to, spell a word or a mathematical equation, now you have order. And that order is information. So how digital information systems exist is by creating and maintaining information. That means by lowering their entropy. If their entropy gets too big, they just become a bunch of random bits, and they don't, they're not really a system anymore. They have no function. They don't do anything. In order to be a system, then they need to do something, and to do or interact, they have to lower their entropy, create, maintain, share information. Well, these systems evolve. So a digital information system, if you have the potential, let's say you just have a potential of a system that can just differentiate between state A and state B, some system, some potential energy that can become aware that there's a difference between state A and state B in itself. Well, that's a 1 and a 0. Then all you need to do is have that system become aware that there can be, multiple 1s and multiple 0s. And then you can put those 1s and 0s in different patterns and orders. And pretty soon you can create information and patterns of these bits. And then you can create time, where time allows you to have a before and an after. You can change things. You see, there is no such thing as change. The word change has no meaning if there is no time. Change requires time. So then time is a new technology to this information system. And with time, it can have sequences of patterns, you see. So it puts a whole new dimension on how it can lower its entropy. It can sequence things. So the creation of time is basically just an awareness of difference, of change, is you can do it this way and then you can do it that way. Oh, well, this way was prior to that way. That defines time. And eventually, in order to make sequences of patterns so that they make more sense and have lower entropy, you want to have regular time. And you have regular time, that means something has to change states, like between a 1 and a 0, 1, 0, 1, 0, 1, 0. Well, that's a metronome or a clock. So this system can what should we say, evolve its own clock, its own concept of time and change, and produce patterns of patterns and sequences of patterns. So that brings us up to something like a digital computer, you see. But this digital computer is conscious because it's able to modify what it does in order to decrease its entropy. Now, it's just evolved to do that, just like the cells. You had cells and they evolved to be whatever, fish and then alligators and then, birds and reptiles and things like that, ending up with people. How did it do that? Well, it just kind of did what worked. You try things by kind of randomness. Things just happen. And if they happen and make you more survivable in biology or more able to procreate, then those things go forward. The things that don't do that, die out. That's the way evolution works. Well, in a consciousness system, a digital information system, things that lower the entropy go forward, and things that don't, things that increase it, die out because they're counterproductive, you see? So you have the same thing. All you need to start with is a potential that can differentiate two states. Now, that's an assumption. You have to start with that as an assumption. Given that as an assumption that a digital information system we call consciousness evolves, that's just a matter of evolution. Just like in biology, we start with an assumption that somehow a cell could create itself just by circumstance and chance, perhaps, somewhere, and after that, we ended up with cells that split and multiple celled and specialization of cells, and everything else follows. So that's assumption number one, is that somehow there was a potential that could differentiate state one from state two. And the second assumption is that evolution exists, and evolution is just a process by which things that work get, go forward, and things that don't go away. So it's a very simple process. All kinds of things evolved. It's not just plants and animals evolved here, but technology has evolved. Lots of things evolve. Monetary systems, governments, philosophy, cultures, they all evolve, and some of them, devolve as well, which means go to higher entropy states, less functional. So that goes on all the time. You have random events that take place, circumstances that take place, and then the system adjusts to deal with it. That's how evolution works. So this whole theory just is built out of those two assumptions. And from those two assumptions, everything else follows as a logical deduction. Okay, so here we have this system, and it's a digital information system. It's trying to evolve. Why? Because it doesn't want to die. If it doesn't evolve, it's going to, get to the point where it's all randomness and not exist anymore. So it's got this dim awareness that we call dim consciousness, sort of like the dim awareness of maybe, an amoeba. So it's not the brilliant consciousness that we think of ourselves as being. This is just a very dim awareness, but it's able to evolve. And it grows and evolves and makes multiple cells and gets technologies like time and et cetera, to where it's now this very bright, this very intelligent digital information system. Now, how is it going to do this evolving? How is it going to know how to get lower entropy? Well, this is a information system. This is a system that does what? Communicates, creates information. So its natural thing to do is the same as biology did. It divides. It what do we call it? Partitions off. It's part of itself, and now there's two of them. Just like a cell divides, and now there's two cells. And these two now can interact and exchange information. Now you've got a huge, larger probability of novelty and new things going on because you've got interaction between two independent things, you see. And then that can happen again and again and again. You end up with lots of individuated units of consciousness interacting with each other within this larger consciousness system. Well, okay, that's what you and I are. We are individuated units of consciousness. And we need to lower our entropy, because if the system doesn't lower its entropy, the system dissipates, goes away, becomes random. So we're parts of it. We need to evolve. As each of the pieces evolve, the whole system evolves, because the whole system is just all the pieces, you see.
Yes, yeah.
Plus some maybe administrative stuff that kind of does the housekeeping off on the side. So we are the system. The system is us. It's all one big system. You may have heard that someplace in metaphysics. We're all one. Well, you see, that's actually true. So here we are, and we're in this, we're individuated units of consciousness, and what's our mission? To lower our entropy, to evolve the quality of our consciousness. Okay, and how do we do that? Well, this is now as a group of individuated units of consciousness interacting with each other. We now have like a social construct. It's chunks of consciousness interacting with other chunks of consciousness. Well, what's the optimum way that a chunk of consciousness can interact with another chunk of consciousness? What optimizes that? What lowers the entropy? Remember, lower entropy means more order. Okay, it's a higher ordered thing, and increasing entropy is less order, more randomness. So you kind of think of one as building and creating, the other one is kind of destructing and dissolving, if you will. So
the way that I learned to conceive of entropy was of things, the kind of directional arrow of time driving things from hot and simple to cold and complex. Yes, that's a pretty technical definition, but that was the original definition in thermodynamics. That's where the term entropy comes from. It comes out of the second law of, it comes out of thermodynamics. And the second law is that the entropy of the universe is always either has to stay the same or decrease. And we know that it can't stay the same. That's not practical in our world, so it has to decrease. But that's a different subject. So anyway, so here we are with these things, and they're trying to lower their entropy. They're in a social construct, interacting with others. And as it turns out, the most optimum way, the most constructive and building way to interact with others is with caring, is with love, is with compassion. And the most destructive way that creates more randomness, that tears down rather than builds up. So construction is more order, is lower entropy. The way that tears down is through fear. Fear creates distrust. Distrust makes it difficult for these individuated units of consciousness to interact with each other. Fear makes an individual say, well, what about me? I need to make sure I have all the things I want. I need, my stuff, as it puts the person at the center.
Yes.
Whereas love is about other, you see. So fear puts a person in the what about me, we call that ego. And love puts a person in it's all about others. It's about somebody else. It's not about me. How can I be of service? How can I help other? How can I help the whole? You see, that's the cell that's now in a multi-celled creature saying, how can I help the whole? What's my part here? It's a cooperative, supportive effort of all the players involved. So that's the low entropy solution. So now we see that here you are an individuated unit of consciousness, and what is it? Is your purpose? It's to evolve. It's to survive. It's to lower your entropy, and you do that by becoming love. So now I'm starting to sound like a Buddhist, aren't I?
No.
It's all about love, you see. Maybe I'm sounding like God is love, sort of thing. But now it's very metaphysical, we see. But now love becomes just a logical consequence of the nature of reality based on two assumptions. One, that consciousness exists. The other, that evolution exists. Out comes individuated units of consciousness who are interacting and optimize their evolution by becoming love, which means by becoming a low entropy entity.
Yes.
So that we've gone now through about 4 or 5 of these paradigm jumps that you have to, and that's a lot, for your listener. I'm giving you a new paradigm jump like every 15 minutes, and usually one of those in 5-year periods is about all we can handle. So one every 50
like I said, I think you'll find we've primed our listener exquisitely. They're absolutely keeping up. They're all showing a huge interest and massive support for the show.
Yeah.
Wonderful description from Tom Campbell. Great guest.
That's good, because if they were just hearing this for the first time and trying to follow it, by now is when they'd start to get the headache.
We've got hundreds.
This is where the pain would start. It starts to get overwhelming because you've got so many new paradigms you're trying to string together in a logical way. So now we've kind of gotten to all these paradigms. So here we are. How do these individual units of consciousness do this? How do they become love? Well, by interacting, right? Well, how do they interact? Well, they could just trade data, but that's a very sterile kind of, abstract kind of interaction. Think of a chat room. Think of a huge chat room, and you got 100,000 people in this chat room, and all you know about them is their made-up username. That's it. You know nothing else. Mm-hmm. And you're having chats with them. Well, what can you get out of that? And let's say there's no rules in this chat room. You can do anything, say anything, you can get away with anything you can get away with. So how much value is that chat room? It's not much value, because you can't depend on anything you get. You have no idea, what's going on. You're starting a relationship with some big lumberjack who lives in the Northwest, and it's really a 12-year-old girl who's playing with you, and she lives in New York City, you see?
Yeah.
You don't know. So it's hard to build relationship in this very abstract sharing data space. So what do we need here? Well, we need something less abstract. So let's create this virtual reality. Let's start this simulation with this little ball of high temperature, high energy, and then let it expand. And we'll let that thing go in the computer until it evolves our universe with our star and our planet and all the other stars and all the other planets, and us too, as probability. See, it's a probabilistic model. So here we are, and it's all probability. And now we're consciousness. We want to interact. We need a place that gives us traction so we can form relationship and learn and grow. Some much better space than this very abstract, just data sharing space. So here's this world, this universe we call physical reality. It's really a simulation inside this larger consciousness system, which is a digital information system. And it's here for the expressed purpose of individuated units of consciousness like you and I to come here and interact with the computer stuff and with each other so that we can learn to become love and let go of fear. Okay, let go of ego. Now, out of fear, you got a bunch of things that kind of drop out of fear. Fear creates ego, like we said. It creates belief, because you have fear that you don't know or don't understand or don't have the answer, and it's an important answer, so you come up with a belief to make you feel better. Fear creates needs, wants, desires, expectations, all this stuff, and that gets in the way. So now I'm beginning to, sound like a whole different class of writers, right? Who maybe Conversations with God, or some other writers like this. Maybe Seth Speaks. I'm starting to take on a sound like a metaphysician, but we've still just done this by logical deduction, if you will, from those two simple assumptions where we started.
Yes.
Okay, so now here we are. We're interacting. We're in this reality where we as consciousness can kind of play a character, right? We can play this character in this reality, and all our character is really a set of rules, things that the character can and can't do. Well, what's the character in The Sims like? It's the same thing. Those characters in The Sims have to follow certain rules. They can't jump 20 feet in the air either, because they're programmed to act like humans. They can't breathe underwater. Your Sims character falls in a swimming pool and some bad girls pulled all the ladders out, like my daughter used to do, and they can't get out of the pool, so they drown. Those things happen in World of Warcraft. If you don't know how to swim and you fall in the water, you will drown. So here you are abiding by the rule set of this game. So whether it's the World of Warcraft game,
the Sims game or the physical reality on Earth game, you know, it's still this physical reality, and you have to abide by the rules, which is the rule set, remember, is our science, has dug out a lot of those rules, things like gravity and you know, Newton's, remember the things we called Newton's laws, you know, those are all basic statements of rules in the rule set. Mm-hmm. So that leads us to, what is our purpose? You know, why am I here? What is my purpose? Big question. Well, your purpose is to lower your entropy, which means become love, which means evolve the quality of your consciousness, to grow up. That's why you're here. And the way this game works is stuff happens. You have to deal with it. You deal with it by making choices. And depending on the quality of the choices you make and how to deal with it, you move closer toward becoming love, evolving, or fear, de-evolving. So if your choice is to get angry and throw a fit, or, you know, draw your gun and shoot someone, or whatever, try to grab all the marbles and run, then you're making bad choices and you're not doing so well in your game. If your choices are on the caring, compassionate side, then you're doing fine and you're growing. Okay, so that's kind of the nature of the reality here. So it's been kind of a long talk. I've got about 10 minutes left at the end, so I think I'm going to throw it back to you, Jack, and see where this summary needs to have patches and holes that I've left in it.
Okay, well, certainly it's been a remarkably complete description of the logical steps that one needs to take from perhaps the assumption that the current scientific model is accurate, to one of realising just how broken it is, and to understanding how more precise, less paradox-ridden the M.B.T model is, and how many different fields it is applicable to, and how in the drawing of those fields together that we may come to an entirely new understanding of our place in the world and our ability to affect our surroundings directly. And I think that that's certainly something that I'd love to get into in the last official hour of this show. My co-host for the 3 hours following this show has graciously given us leeway to take as much of the music show as necessary to complete this subject. So we do have free rein here. But one of the very, very minor, almost feel foolish even bringing it to the table, because it's really only an issue of semantics, of the use of language. But one of the issues that I've had with many of the concepts that have required the use of the word love is that in the context of M.B.T, I personally see a kind of a more precise description of what's actually the action through reality that's being described there is more a beneficence. Because when I see, the universe is love, that for me doesn't explain the whys and wherefores of, say, warfare. Whereas beneficence would then allow for, if the warfare was more beneficial to more people and acquired more novelty as a result, then it would be seen by a benign universe as beneficial.
Mm-hmm. It's interesting that we end up in this theory with things like love having a technical definition. You know, love is one of those things the poets say cannot be defined, but in this system, love is an entropy measurement, right? It's a low energy being is love. So what's your love quotient today? Well, it's like saying what's your entropy level today, as far as a individuated unit of consciousness. So love becomes.
Oh, I'm sorry, Tom, you just dropped out.
When I was developing the theory, I thought, well, isn't that nice?
Tom, sorry, you just dropped out for about two or 3 seconds there, just as you were finishing your last sentence.
Okay, I thought that was particularly interesting when I finally got to that point, that love this kind of magical word that means so many things to so many people actually has a very precise and technical definition in terms of entropy.
Yes, absolutely. Well, there's certainly, like I say, it strikes me that in a universe where, you know what I mean, an asteroid can wipe out the majority of the life forms on the planet at some point in our digital history, surely that can't necessarily be seen as an act of love, and yet it would have driven the vast expansion of biological evolution immediately prior to that mass extinction event. And then surely one could see that as not necessarily a loving event, but certainly as a very beneficent event.
Mm-hmm. Exactly. It's the way that morality boils down in this scheme is that, you know, if you want to know whether something is moral or not, it's whether or not it lowers or raises, you know, the entropy of the system. So that's basically it. If what you're doing is, or what is happening increases the entropy of the system, then that's bad. That's dissolution. That's de-evolution. If it decreases the entropy of the system, and I would say that in a long term, you know, if it's a long-term decrease, then that's good. So now we also have a technical definition that defines what's good and bad and what's moral and immoral. And in fact, my son, when he was in college, he's a philosophy major, he took that concept out of M.B.T. and developed an entire ethical system based on it, which is the only ethical system I know that so far answers all the mail and doesn't have any fatal flaws in it.
I have read that on your website and would strongly advise anybody wanting a grounding, possibly even something to show to your children as a means of giving them an appropriate moral grounding without the need for religious or sociological or cultural dogma. It's a superb work.
That's a real neat thing, because here we have physics deriving ethics and morality. You know, well, how is that? See, that's one of those neat things that when you really do understand what's going on and how it works, everything kind of comes together, and everything is really a part of everything else. So here we have ethics and morality and love, and all of them are derived out of this kind of fundamental physics of a virtual reality and consciousness and the probability models. So it's a neat thing where all of these things that before were like unrelated and disparate things that just don't go together, like science and, you know, like physics and metaphysics, you know, like science and philosophy, they're at opposite ends of the pole. Find out they're really not opposite ends of the pole at all. They're just all different viewpoints of the same thing. And a good understanding, a good physics drives them all, you know, derives theology as well as explains the double slit experiment.
Like I say, removes the mysticism from what are experienced events for many of us. With you, with the transcendental meditation, for myself with the temporal lobe epilepsy, which with experience that falls outside of the model that we're given. In the absence of that larger model, we have to go seeking that model. And in my mind, you have constructed an absolute paradox-free working model that we can all use in a practical sense as well. And perhaps that's something that we can come on to in the next hour, is the practical applications of M.B.T, which in my mind are just mind-boggling.
Okay, we're almost to the hour, aren't we?
Yeah, absolutely. I've got a song lined up, so if we'll go to that, because it's a convenient point, give our listeners another comfort break. And ladies and gentlemen, we'll be back with you immediately after this tune and on around about the hour of 11 o'clock GMT. Okay, we're back with Freeman Jack and Bitchin' Bob with Dr. Thomas Campbell live from America. Been an absolute cracking show so far, and we've got some sort of Q&As lined up for Tom, which will hopefully just blow the lid off this subject even more and explore the parameters of this subject. So I'd like to sort of title this last hour or last segment Practical M.B.T. or Practical Plastic Reality. And one thing that Bob was just asking there was the implications of the search for the Higgs boson. Bob, do you want to ask Tom your question?
Yeah, sure. Tom, no, I was just asking, with the search for the Higgs boson being, big headlines recently, whatever, a major event, could that outcome of the Higgs search be biased by the scientists' collective intent?
Absolutely. If you have a whole lot of people with an intent that things are going to be a certain way, then if they can meet the conditions of being that way, and we can talk about that in a minute, then certainly it raises the probability that they will be that way.
Yeah.
So we have a very plastic, a very fluid reality because it's a probabilistic reality. It's not a deterministic reality. It's probabilistic. And there's just a couple of criteria that you have to meet in order for something to be possible here. And that is that something that comes into this reality, one has to obey the rule set. So we don't have things that flaunt the rule set, because it's like The Sims and World of Warcraft. All the characters and everything that happens in those games have to abide by the rules. Secondly, there has to be historical consistency. So you can't have a discontinuity in history. You see, there needs to be a continuous history. So the things in the past have to affect, the things that happen next. So you can't just have, you can't go into your house in London one day and then turn around and walk out the front door and, you're in Germany or Australia or someplace. You see, that would be a big,
nothing.
Yeah, that's a big discontinuity. So you can't have that. You need to have, consistency in the history, and it has to abide by the rule set. Now, actually, that's just one criteria. I list that as two, but if it abides by the rule set, then it must have consistency. I mean, consistency will be there if the rule set is obeyed. So it's really just that one rule, but I like to put it in two different parts because people can conceive of it better that way. So anyway, as long as having a Higgs boson doesn't violate either of those rules, if there could be a historical consistency, and there could be, because there's nothing that says it's impossible, then all we have to do is have it be consistent with the rule set, and then it's possible. And if it's possible, if you have a lot of intents focused on its happening, then its probability of happening goes up. Yeah. So this way, we're creating this reality as we go. You see, this reality we're in is a continuing work in progress, and we continue to create it as we move through it.
And would you suggest that it would be a powerful influence on the probabilistic future reality field of investing? I think it was 11 billion, wasn't it? 11 billion euro in the Hadron Collider.
Sure, that might raise that probability too. A lot of people hopeful, and an awful lot of physicists basically gambling their entire careers and works on the back of that. And there's some people who don't like it. There's those people that say the Bose particle is not necessary. There's other ways to solve the problems, and they think that it's not so likely, and that would be kind of weight on the other side. And besides that, there's all sorts of things the larger consciousness system might want to do with it. It might want to, it may think that it would be good for the whole if, after spending those billions of dollars, they come up with, they're forced to go to a different worldview instead of continuing this particle worldview that they have. Right. So it may turn out that more particles into the particle view of the world, which we know is not an accurate view of the world. The world isn't particles, it's probability. Double Slit told us that. Mm-hmm. So it may be that it's time for a big goose egg to push thinking in another direction. Well, if you just did that and spent $1,000, nobody would care. But if you do that and spend a few billion, then that gets everybody's attention. So hard to say how it'll come out. There's lots of things that are probably pushing that probability one way or another.
Well, I tend to think of it in terms of your work, especially the discovering of the mass of the Higgs boson will be akin to knowing the precise weight of your Sims character.
Science is kind of, because it doesn't understand the nature of reality, they tend to work themselves, paint themselves into corners, and then they have to come up with these extra, you'd call them fudge factors, I guess, if you're on one side. If you're on the other, you'd call them discoveries. But they come up with these fudge factors that allow them then to maintain the fiction of an objective reality. And things like, dark matter. You see, that's one of the equations don't balance right if you don't have this other big, force someplace. And because the equations must balance if you have an objective physical reality, then you can make something up to force them to balance, and you call it dark matter. Now suddenly there's a whole another thing out there, and all it is it's a concept that enables you to continue to use the same model that you've been using to this point. So they get to points like that, and they have so much belief and confidence in their model that if the model requires dark energy to work, then there must be dark energy, and then you go off on a search for dark energy. And indeed, like you say, if that's not impossible, you may even create it. So it's a real squirrely world we live in, and there's lots of possibilities. And physicists are kind of infamous for making things up to get them out of the corners that they painted themselves into.
Okay, sort of on the practical side, just before we came back to air, I was saying how before coming across your material, I was essentially living an M.B.T life where I learnt at a very early age that I had the ability to project police cars into my path to pull me over and to inquire about the contents of my pockets as a youth. And I learnt at a very early age how to stop projecting police cars into my path because of the frequency with which I managed to make it happen. And without the construct to explain that, again, I reverted to mysticism and took it on board as a belief simply because it worked. But again, you're bringing a description of this kind of probabilistic, statistical future reality field where our beliefs in the here and now will actually have a direct impact on what comes our way down through that sort of probabilistic pipeline. Would you like to kind of expand on that?
Yes, and we see that all over, in all sorts of fields. Basically, that's what's going on over at Princeton, at Pear Labs, when they have people using their intent to skew, distributions of things like, we were talking about the Geiger counters, things like that. That's that intent that's modifying the future. We also have that we've known things, educators have done some research that says that if the teacher is told that their students are particularly bright, their students will actually do better, end up doing better on standardized testing, just because the teacher believes that they're bright. And if the teacher believes that they're substandard, that they're not too bright, they will end up doing worse. And if you actually tell the students that as well, they'll do much better or much worse. So if all the students are told, you're the slow group, things are a little hard for you, so we're going to try to make it easy. We're going to put you in this slow group. Then you'll find out, even though they were just average students that were picked at random from the student body, you'll find out they will do worse. So just the teacher by herself by himself will make a difference to the outcome of the class. In other words, the class won't score as well on their standardized tests, won't do as well as far as their intellectual capacity goes. And
to my mind, Tom, something that you illustrated, I think, in the Calgary seminar, that the conviction of an oncologist in his ability to cure his patient's cancer has a direct impact on his statistical liability of curing his patient's cancer.
Absolutely.
And you go further than that to actually suggest that the reality of the cancer doesn't collapse out of the probability field until your doctor tells you about the existence of that cancer.
Yeah, see, that's the way this reality works. It stays just like the particle, just like this electron. They stay potential particles. They're just probability, a probable or potential particle until the measurement's made. So it's just a probable or potential tumor until the measurement's made. Once you make the measurement, that collapses the probability to a tumor or not, because now you've got the biopsy, and when a guy looks at it under his microscope, it's a tumor or not. So you've taken the measurement. But up until that point, it's just probable. Now, it may be very probable, or it may be slightly probable. Probable just means that it's not a done deal. It's not fixed. It's not an objective fact. But this is also done. We have a thing called the placebo effect. Talking about medicine, where you give people, medicine that isn't medicine. It's sawdust or sugar pills or something that has no medical value. But you tell them that it's a terrific cure for what ails them, and they get better. And it's not that you're just fiddling with their minds and they think they're better or they pretend they're better, but they actually get better, against a control group that wasn't told anything like that. So the placebo effect is so integrated into our medicine that medicines generally cannot be sold to the public until they have beaten a placebo test. And that's getting harder and harder for the drug companies to accomplish. They have to go to other cultures in order to get their drugs to beat the placebo test.
Well, I was going to say, to that point, Tom, had you heard that the placebo effect has actually multiplied fourfold in the last decade?
That's correct. Yeah.
That the placebo effect is now 4 times more potent than it had been at any time in the previous decade.
Yeah, and part of that is our belief in medicine. Now we have our televisions are full of commercials about, take this drug and you'll live happily ever after. Take that drug and your heart problem will disappear, and so on. So we've built up all of these expectations. Well, that's just like telling somebody that this sugar pill is going to, help them get better. We build up so many expectations and such a confidence that science can cure it. Science can cure everything, anything we can imagine. Want to travel in time? One day science will figure it out. We have this irrational belief that science can produce all the answers. And because of that belief, then the placebo effect, we get particularly susceptible to that. We find all these claims very credible, whereas other people do not.
And also the nocebo effect, the contradictory state to the placebo effect, the effect that causes whole cabins of airline passengers to fall ill because somebody's been heard being sick in the toilets and the fish was served for lunch, and the whole cabin will suddenly start to be sick, and there'll be no physical cause.
Yes, that happens as well. Now, another a study that brought to life a fact that the doctor's bedside manner will make his ability to heal greater or worse. So those doctors who actually kind of relate to their patients as human beings, give them encouragement, explain what's going wrong, pat them on the heads and become part of their healing thing, rather have better healing rates. They cure people better and more often than doctors who say, well, you got this wrong with you and that wrong with you, probably won't do you any good, but you can try this medicine. If they have that attitude, then they don't have a very good healing rate. And they found that just that by itself made a difference between a good doctor and a poor doctor.
Well, a question I want to ask you there, Tom. The good intent, is that would that explain, well, in your opinion, I don't know whether you're a religious man or whatever, but, with religion and you get so many people praying in prayer groups and they've had positive outcomes and definitely influence. Is that not just another example of the good intent? Yeah.
That is exactly another example. So is it, the psychic healing. You can heal with your mind if you can focus your intent for that outcome. Mm-hmm. So it explains all that sort of thing. It explains synchronicity, that things just happen at the right time, at the right place, in the way you expect them to happen or the way that you need them to happen. It explains things like, the power of positive thinking. Those people who are just positive and they go about life positive generally do much better than those people who are negative and go about their life in a negative, woe is me, everything happens to me kind of attitude. It usually does happen to them.
That's
people who are very fearful end up, if maybe they're fearful that a policeman is going to come out from behind a hiding place and catch them, like Jack there. If they're very fearful, they create that situation. Yeah. So absolutely, you have a whole program that just, some years ago called The Secret, which had to do with, quote, programming the universe to give you whatever you want. And that is basically the same sort of application. It has nothing to do with programming the universe. I mean, what does that mean, programming the universe? It basically has to do with modifying the future probabilities to change. You have control over that, of what happens. It just means you can modify the probability. So if that probability started out to be 10 to the minus 10, which is 1 in what would that be? 1 in 10 billion, which is not very probable. You might work real hard at it and get it all the way up to, just 1 in a million, which is still not very likely, but you've moved it a huge amount.
Could we possibly do like an idiot's guide to affecting the future probability field?
Well, sure. You want me to kind of tell people how to go about doing that?
It would be nice to at least personally, I find that to maximise the effect of intentionally acting upon the future probability field is, like you say, to be acting from love, essentially. And that if you're acting with, again, I use the term beneficent intent, and if your view is outward, then generally speaking, it would appear that the future probability field is happier to reward that. And so from that perspective, I would suggest that, yes, it is possible to affect your future outcome, but that the effect seems to be much greater if you're wanting to do it for the benefit of somebody else, or even more so for everybody else.
Yeah, and the reason that's true, that is one of, there's several parameters that make it more or less effective. The one you just mentioned, it's more effective if your intent is a loving intent, and the reason for that is the consciousness system is about decreasing entropy. It's about becoming love. And if you are doing things that are requiring the system to work against itself, in other words, to embellish ego, to embellish fear, you're using your intent to create more ego and more fear, then you're asking the system to work against its own best interest, to work toward its de-evolution, and the system won't like that, So the system's not going to be very helpful there. Whereas if you are asking it to do things that are moving the system toward more or better evolution, then the system will want to encourage that. Now, we talk about the system encouraging or discouraging. Well, this is an intelligent system, right? This system has evolved and able to produce virtual realities that we can play in. This is not a stupid system. So using it to aggrandize your ego, often, that's going to come back and slap you in the face. You might actually get what you want, but you may get it in a way that you wish you hadn't started the process.
Indeed.
Why? Because the system is likely to want to teach you a lesson that will help you eventually lower the entropy of the system rather than raise it. So we have a couple of things in play here. One is the system and its willingness to help. Two is your intent and how focused your intent is. So if you just make a wish, oh, I wish I were rich. Oh, I wish, I didn't have to walk so far to get to the store. These kinds of things, that's not going to change much. You have to first learn how to get the noise out of your mind so that your intent can be clear and well-focused. Your mind's not flying around. So that's one of the parameters. Another parameter is that you have to realize that what you're trying to change has its own natural probability, and you can only change things within that natural probability, and you can only move them so far with your intent. It's also cumulative. So if you work on this thing, 10 times a day, you'll be 10 times more likely to move the probability than if you work on it once a day. Or if you get 10 people together, we're talking about the prayer circle, 10 people together to focus their intent on something, then you're going to have, if all 10 of them are equally capable of focusing and clarity, then you'll have 10 times the effect if you have 10 people working on it. So some people are tremendously more focused and clear than others, and some, so there's a lot of variables in play, I guess.
And then to empower those two other forces, shall we call them, you also have the example, like we say, of building the Large Hadron Collider as being a vast material input and external input into that belief field. And that this is my thing, is that as well as having that sort of fixed intent and the belief and the focus in the first place, that you have to act externally with these things in order to empower them into the real world?
Yes, you have to act. Yeah. Well, what you do when you focus and what you use your intent, you're not forcing something to come into our virtual reality. You're just raising the probability that it will come in to our reality. Now, then it gets to the point of, well, what was the probability to begin with? If it was, if it was almost enough to get into reality, then your nudge will be enough to make it go. If it was extremely unlikely, then your nudge may or may not be enough to make it go, or you need a more powerful nudge.
Well, you have a fine example in one of your talks about securing a parking place if you're going to the theatre of an evening.
Yes. Mm-hmm. Dennis Menerick gave me that. That was the fellow that I mentioned earlier, as he and I started out, with Monroe in the beginning of Bob building a consciousness research facility. And Dennis said that one of his favorite things to do was to produce a parking space for himself, because where he went to work was in an urban area. There were probably only a quarter as many parking spaces as there were people that wanted them. So a turnover was very quick. A car would pull out, and within 10 seconds, somebody else's car would pull in, and that's just the way it always was. So it was very hard to get parking spaces. And he would start out in the morning, before he even left home, in his mind, using his intent to create the situation where just as he got to the street in front of his office building, somebody would pull out and he would be able to pull in, that a parking space would just become available just as he got there. And he found out that it was about 80% he could arrange that. And I imagine the other 20%, it's because the situations were not such that the system could manipulate them to give him that parking space. In other words, the probability was too low to begin with, that couldn't successfully be manipulated. But with, say, 50 or 60 cars in his view that he could pull out and give him a space, there was generally somebody who was maybe just about thinking about going, that that changing that probability would just hurry them up a bit, just kind of move them on their way, so they just got there at just the right time. And that sort of thing works. People call cabs in the same way. They'll go out on the street and they'll have an intent that a cab will just be, just around the corner. Will be coming by any time now, and it makes a huge difference in whether or not you get a cab.
I certainly have completely stopped believing in London's traffic and its ability to gridlock. I spent years convinced of London's entire ability to gridlock on a regular basis, and subsequently spent my entire life driving in London gridlock. Having convinced myself of its non-existence, I frequently find myself driving across London as if it's 5 a.m. in the middle of the rush hour.
There you go.
So these are kind of practical applications. We've got a real sticky subject arising in the chat box. We have a few incredulous minds now that we go slightly deeper into the subject. I mentioned in answer to somebody's question that your thoughts create external objects, and our 100th monkey came back with that he can't agree, and that why do I say that it does? Well, perhaps Tom may be better at explaining how your mind literally creates the stuff and substance that you think of as reality and external objects.
Okay, well, again, your mind, your intent creates a change. You can raise or lower the probability of something happening. So let's put it that way. Now, if something is not likely to happen, like let's say you are outside on a very hot day in the middle of the summer, and you would like to have an ice cube appear in your hand, you see the probability of that happening now isn't very high. So even with a lot of intent, you probably aren't going to make that happen. Now, it doesn't mean that it is impossible. It just means the probability is low. See, almost nothing is impossible. Things are just improbable or very probable. So in that case, if you had someone who had very, very strong focus and intent, maybe they could do that, but there would be restrictions because we have this thing about consistency, right? They couldn't do that, let's say, if they had invited all the cameramen from the news to come down and watch this ice cube appear in their hand. They would not be able to do it because now they would be creating a discontinuity in the rule set in public in front of lots of people, and it wouldn't work. Now, if they could go someplace private where nobody was looking and they had a lot of their own personal clarity and focus, maybe they could do that, but nobody would believe them because everybody said, oh, you're just making that up. And now suddenly the probability of doing it, you see, increases because they don't have this added inconsistency issue, you see. So probability can go up and down based on circumstances and go up and down based on the individual. So if we have something, we don't say that anybody can make anything anytime they want. It's not like that. It's just that the probability goes up and down with various things. One of the little things I do in my talks is the man in the woods, and this maybe will give you some idea of how things are created or not created. And it's a simple little example, and that is that you have a person walking into a woods that nothing is in. So this is going to be a virgin woods, doesn't have any bugs, doesn't have any critters, doesn't have anything. It's just a woods. So this is not a practical thing. This would not actually occur, but it's a thought experiment. All right,
theoretical woods.
Yeah, it's a theoretical woods. It's a thought experiment. So we just have this woods. And why is the woods there? Well, the woods there is because it's probable. And this person walked over this land that nothing had ever seen before and popped over a little hill and looked, and there he saw a woods. The reason he sees the woods is that it's probable that woods were there. So when he looks over the woods, the system has to give him some data. He's taking a measurement. What is he going to see? Well, there are maybe a lot of things that he could see that are possible, and some are much more likely than others. And when he makes that random draw, he picks one, and let's say that it's a woods. Now, once he sees the woods, the measurement's been made. They know it's like which slit the electron's at. After that, it has to stay in this reality. So now there's a woods there. All right, so he walks over to the woods, and let's say he walks into the woods, and what is he going to see? Well, again, you see, we do this whole thing over again. What he sees depends on what's likely, what's possible and what's probable. And of all those things, there are distributions. When I talk about distributions, think of like a histogram under a probability curve. What that means, we can do this in a simple analogy so you'll get the ideas, because I'll keep using this word. You know, you reach up and take a random draw from a distribution. Most people, their eyes glaze over and they don't exactly know what that means. But think of, we have a distribution, and let's say we'll say this distribution will be reduced to the number of let's say the number of pieces of paper in a hat. We're going to do like the random drawing by picking a piece of paper out of a hat. So in this particular distribution, we're gonna pull and see what is likely to come out. And let's say there are 1,000 pieces of paper in this hat that have the number 100 on it, and then there's maybe 500 that have the number 20 on it, and maybe there's 20 that have the number 10 on it, and maybe there's 1 that has the number 1 on it, you see? So that's your distribution, all those numbers of things. That's how those numbers are distributed in there from 1 to 100. So when you reach out and just take a random distribution, what are you most likely to pull out? Well, 100. There was 1,000 of those in there. Pulling out the 1 piece of paper that had a 1 on it, there's only 1 of those in there. So it's one in. You have to sum up all the numbers of papers we did. So let's say there was 1,000, then 500 in them. So there's about, say, 15 or 1,600 in there. So it'd be 1 out of 1,600 that you'd pull that 1 out. Mm-hmm. So that's what I mean by taking a random draw. So some things are more likely than others, and you take a random draw about the things that are likely. So you walk into this woods, and you take a draw, and you say you see a certain set of trees, certain kinds of bushes. You know, was it a deciduous forest, a conifer forest, whatever? That has to do with the probability, what's likely to be there. Okay, so you take that draw, and then you come in and you say, well, here there's a dead tree in this woods, just off to my right where I walked into the woods, and that dead tree is about to fall over. So that was just a random draw of defining the woods. Mm-hmm. So now you walk out of the woods. So that woods is going to be there. When you turn around and come back, you'll find the same woods. You walk back in the woods, you'll find the same dead tree, and everything will stay the same. That's because you need consistency. Okay, but let's say now in this, to kind of give you an idea how this probability works, let's say this person walks out of the woods after seeing the dead tree, and he comes back 5 years later, and he sees a tree laying on the ground. Did the tree fall over? Well, no, the tree didn't fall over. When he was gone, nobody else looked at these woods, so these woods weren't being rendered. There was no reason to render the woods. The only reason you think the woods had to consistently be rendered is because you believe reality is objective and physical, and everything that's there has to be rendered all the time. It doesn't. This is a simulation. Okay, this is a virtual reality. Your people walking around in The Sims and in World of Warcraft don't have the whole map rendered to them all the time. Only what they're looking at. The computer, the server, only sends data out if there's a character in the game looking at something. So let's say there's no characters in the World of Warcraft game. There's just this 1 minute when nobody's there. What does the computer send out to people? Well, nothing. There's nobody there to send it out to. So it's not rendering anything. It's just potential in a computer. Then somebody signs on and they pop up in some area. Well, then it renders that area to them. You see, that's the way the system works. So when he comes back later and he sees the tree on the ground, did the tree have to fall over? No. The tree then gets rendered on the ground because that's likely, because before it was dead and wobbly, and it's the probability of it having fallen over because of storms and other things that are probable in that area was such that when he pulls that random draw out, now when he looks, he finds a dead tree laying on the ground. So no, it didn't have to fall over. Once it's rendered standing up, the next time he looks, it's rendered laying down. You see, so that's just the way it works. Now people get confused with this, and they say, well, okay, there's a tree in a park, and all the people go home and go to bed, and nobody's looking at the tree. Does the tree disappear? Well, of course the tree doesn't disappear. The tree was never there in the first place. You see, the tree is just data that's being sent out to individuals. If there's nobody there looking at it, then there's nobody to send a picture of that tree to. There's no user online to send to render that tree to. So it's just not rendered. Now, if somebody gets up and goes, looks, then that person has a tree rendered to them. If they set up a camera, then that camera sees the tree all night long sitting there. That's rendered. Okay, that's part of the reality.
Can we move Can we move from here into the effect that consensus and how objects that appear to be sustained through generations, how those objects may be rendered into reality consistently, and how perhaps that's driven by a degree of cultural consensus about that reality. I was thinking of the, everyday objects like tables and chairs, how they remain tables and chairs without necessarily the observer to create them.
Well, once something comes here, like once that electron is measured at a particular slit, then that electron just keeps, can only then act like a particle that's physical in this reality frame. In other words, it becomes information within this reality frame, this physical frame, and it has to act under the way the rule set would have it act while it's here. It can't violate any of the rules. So it's the same with everything else. If there's a table or a chair or a thing and it's here because it's being rendered here because somebody built it, somebody bought it, somebody's sitting on it, whatever, then it's rendered here. It can be used just like things rendered in the video games that we play. And, it can be passed down from one family to another because as long as it's here, it's here. So what's the probability? So let's say you close the door, everybody leaves the room and there's nobody in that room. Well, is there any reason for the system to continue rendering that table and chairs that are in that room? Well, no. But that doesn't mean anything. When people walk back, it gets rendered to them again. You see, it's not like, well, they're there and then they disappear. They're not there and disappear. They never were there. We're just talking about data. This is a virtual reality. There are no tables. And tables are illusions.
And this is a wonderful explanation as well as to how things like car keys can appear to migrate. And that you've got a wonderful term called strong history. And that the car key conundrum is largely driven by the absence of a strong history about where you last left them.
Exactly. If you have car keys or glasses or things and you don't know where they are and you're looking for them, okay, and if you really don't have any idea where they might be, then where you find them, how does the system decide where to render them when you go to find them? Okay, well, it doesn't know because there isn't any strong peaks in the probability distribution. If you say, well, I hadn't been in any of these rooms all day. I've only been in these two rooms, so it's not in this one. It must be in the other one. Now there's a pretty good probability distribution that's headed for having it in, one of those two rooms because you just haven't been in any of the others. But if you don't have that sort of probability, and it's just as likely that they're on the nightstand in your bedroom or in the drawer at your desk, then it's kind of a random draw there, and you could get one just about as easily as the other. So you think it's odd that you put your keys down someplace, and then it's random where they turn up again. That's just because they have a weak history. Remember, we only have to satisfy this idea that the history has to be continuous, you can't have history jumping around. And if there is no history, then there's a bigger uncertainty, and reality will accommodate that larger uncertainty with a wider range of possibilities. So that's why that works. So when you lose your glasses and you look and you can't find them, that may be because they're, you just don't remember. There's no data anymore where they are. And particularly if the system is trying to convince you that reality is larger than you think it is, so it's going to do a little demonstration here, you may find them in one of those rooms that you didn't go in. And then it's like a big mystery. How did that happen? How could that be like that? I found them so-and-so, and I never was there. Well, the idea is that, reality is stranger than you think. Strange things can happen. I've known people whose stuff disappears and then reappears in in drawers and places.
I've experienced it personally.
Yeah, just part of their life. It happens that way. Well,
Tom, I'm mindful of of suffering from patricide after the show if I don't ask this question. It's been posed by my 20-year-old son, who, like I say, introduced you to me via your YouTube work, and so, like I say, has shown possibly a more intense fascination with your work than even I have. And his question is around the subject of out-of-body experience, and again the practical applications. And he's asking what are the possible benefits of out-of-body experience, and if more could be learnt about physics in the out-of-body experience than necessarily in so-called real life.
Well, kind of yes and no. There's more to this question than just a simple answer. First, let's say that out-of-body experience is unnecessary for growing up and evolving in the larger conscious system. You can do that. What's necessary to evolve and to grow is that you become love. That's the key. You lower your entropy. And if out-of-body experience can help you do that, in the sense that it can show you a bigger picture, which opens your mind and lets you see kind of a larger view, but it doesn't have to be. Some people get there even though they don't have a larger view. They still get to the point of becoming love, even within their constraints of a smaller view. So you can evolve in almost any circumstance and any surrounding. So I'd like to make that clear. Sometimes people say, oh, doing these paranormal things is the only way to grow up. I need to get these powers. Well, that's mostly ego speaking. It's not necessary. On the other hand, if you're curious and you'd like to find out about things for yourself, then remote viewing or out-of-body experience is a real neat way to demonstrate to yourself that reality indeed is just informational and it's probabilistic. And you can do this in many ways. You can get to an out-of-body state, or, again, remote viewing, or just a meditation state. The differences between these states are more a function of belief and the restrictions that you put on them than there are actually any real differences between them. It's more of the direction that you get to them from than it is anything unique about the state itself. So when you are connected to the larger consciousness system, let's just put it that way instead of calling it remote viewing or out of body or lucid dreaming or whatever. If you're connected to the larger consciousness system, then you have access to a tremendous amount of information that you don't have access to here. It's not information that's in this physical reality. Part of the way this reality frame has to work, part of the mechanics of it is there is this future probable database, which we've been talking about. There's also an historical database, which is all the data of everything that did happen and everything that could have happened but didn't, and the probability of it happening. So we have these databases, and from those databases, you can glean great deals of information. When we look at somebody's aura and we see that aura around them, we're just getting data from these databases. When we do let's see, what's the word, diagnosis of somebody, okay, we're going to look at somebody's health aura or health energy body or whatever we want to call it. These are all just metaphors. You want to look at somebody's health energy body, then what you're doing is focusing your intent on this information. Your intent is like the query into the database, and you get information back. If you can lower the noise of your mind, and if you can get through all your limitations of your beliefs, et cetera, and you get this data back. You can also get technical data. You talk about, can you learn physics there? Well, I came to my theories based on experiments done in the larger consciousness system. The only way to tell that historical database is not, can we say, it's animated all right. It's just like being there. It's like, watching a movie or being part of the movie. But you find out that there's no free will in it. It's just history. It's history and probability. There's no free will in that database. Yes, you can go there and have discussions with people who have lived, but you're only getting the history and the probability view of it. They don't have free will. And how did I find that out? Well, I had to do experiments there. I had to change variables and see how the change of variables resulted in changes in the answers. And you do enough experiments, you can learn things about how the system works. So you can do science there. Your experiments are repeatable, and you get, real information. And if you are a left brain kind of person that likes to deal with the world in logical, structure, then that sort of thing may be appealing to you. If you're a right brain person and you kind of deal with reality in wholes, in big chunks, you probably don't like logical structure, and these sorts of things are probably not all that interesting to you. You kind of don't need that structure. You just jump to the big picture conclusion without having a logical pathway there. But I'm a physicist, so I'm a scientist. I like logical structure, and that's why I kind of took that particular route. But all of this information is available. Now, again, just like we were talking about, it's available to you, but if you misuse it, if you try to use it and gather it for reasons or intents that are focused by your ego, good information back. The system doesn't necessarily have to cooperate. You have a system, but the system is intelligent. It's not a dumb system. It's intelligent and it's evolving. So you also have to interact with the needs and wants of the system if you want, which is basically to lower its entropy. So there's some variables in there that make it a little more complicated than just you're the only actor and the system is like a big machine that must respond to you. The system can respond to you in different ways based on its sense of what's good, for lowering entropy of the system. Does that answer the question, or do you want me to?
No, I think that answers it. I think that will answer it admirably. Thank you so much, Tom. And you covered so many subjects tonight, and even in really just the last 10 minutes, you've kind of touched on so many of the themes that run through your seminars on YouTube. I know you mentioned in an email that you would consider coming back for later shows. Would it be possible to put you on the spot now and ask if you would consider coming back for more shows later on?
Sure, absolutely.
I'm minded that, like I say, it's late here in England, and our listeners are beginning to be eroded by the late hour, and I'm minded that we've already had you on for nearly 3 hours now. Would it be possible to kind of book you for some more of these 3-hour sessions, and possibly use each one to explore more fully the realms that you touch on of remote healing, remote viewing, and I heard you talk about suicide earlier, and that's a particular matter that's very close to my heart, and a large part of my broadcast is trying to prevent suicide under the current kind of economic climate. And
we can talk about some reverse causality. That's something that often is very interesting. Those 2 Geiger counters we were talking about earlier, that the people at Pear Labs can change the amount of counts, or the ratio of counts in the two Geiger counters. They can take that data, and a year later they can use their intent to modify the information, of that old data. And that's called reverse causality. It's not really reversing causality at all. It just has to do with the statistical probabilistic nature of the universe. And those have been done many times as well. So there's a lot of things to talk about, a lot of applications that are kind of fun.
Well, Charlie says thank you for the answer. So I assume that means that you answered it adequately to his satisfaction. Bob, I'm minded, have you got any other last questions that you're desperate to get in with, Tom, before we hit the top of the hour?
Well, actually, I'm very interested in whenever you were talking about OOBE and whatever, and it was a question that had been asked by one of our regular listeners who can't be present tonight, and he did say if I could get a slot in with you. He wanted to know about the pineal gland, and does any of your research, from Monroe laboratories and whatever, point to any connection between it and consciousness?
Well, remember, the pineal gland is a virtual pineal gland, just like you have a virtual brain and a virtual body. Okay, right. And the pineal gland then is a part of that evolved system that we call physical, that simulation that defines the what we can and cannot do and the structure of our physical world. Mm-hmm. So it's a physical. It's a virtual pineal gland, but it has ramifications about what the body can do and what the body can't do. So it's connected to what the body will support. In other words, your mind here in this physical reality, as a human in this physical reality, you are constrained by what the rule set will support, and that constraint is in the form of your body. Okay, so like I say, you can't learn difference equations and advanced calculus all in 5 minutes, because your brain just can't do that, because it's limited by the rule set of how it evolved. Well, your pineal gland gives you certain capabilities, and if you get rid of it, some of those capabilities are gone, you see. So yes, the pineal gland is a significant gland. It does affect the way the brain processes information. Well, I didn't say that right, did I? It's a virtual brain. The brain really doesn't process any information. The brain just develops the constraint, in other words, the capacity that you have for processing information. The information is all processed in consciousness, not in a virtual brain. The virtual brain just sets the limits of what can and what cannot happen. It's part of that virtual simulation that we're in. It's a very complex thing to describe very quickly. Maybe next time we'll have more time. I see we're within minutes of having to.
Oh, really, don't worry too much about the hour coming up. Like I say, we have an entirely fluid schedule here. Like I say, I'm really concerned for your voice and for the listeners' brains, which I'm sure must be letting off a little steam by about now, and hopefully we've shifted so many paradigms so far that it will take a week or two for us to be able to shift them any more with any significant force.
I find that people tend to get this in little bits. So I have people that have read the book 7 or 8 times, and each time they find stuff in it that they never found before. And that happens with the things on YouTube. They'll watch them, and they'll watch them again, and then they'll watch another one that's similar, and then all of a sudden they hear things that just didn't click before, and they think, well, I've never heard that before, but yes, they did. They just weren't quite ready to make those connections yet. So it is an iterative process.
Well, funnily enough, I described the most peculiar experience of watching your videos, and the only other time that I've experienced it has been reading 2 books, both of which were of huge significance to me. One was Anton Wilson's Illuminatus, and the other one was James Joyce's Ulysses. And both of those books had the effect of transporting me, that I couldn't actually stay within the confines of the plot or the page, but that the information that was being given to me would take my mind on such wonderful journeys of its own. And I often find myself watching your videos and just going off on a complete kind of logical sort of tangent, and then finding myself kind of drifting gently back into what's being said, realising that I've probably just been away for 10 minutes.
Yeah, kind of listening at the being level rather than at the intellectual level.
It's certainly an interesting effect that I can only imagine must come from, all 3 of you having thought very deeply about your subjects. It's the clarity with which you express them as well. Both myself and Bob have been taken by the simplicity. Obviously, there's a level of jargon that has to be required when you start to use sort of quantum effects as your proofs. then it's very hard not to descend into the sort of scientific jargon. But in essence, your explanations can be condensed into a simplicity that really any 12-year-old should be able to grasp. And like I say, with practical applications that if we apply to our every day-to-day life, I think we haven't even touched on the matter of beginning to become monitor of your own thoughts and careful of what you wish for in some degree, and the potential power of collective thought, where if perhaps the more minds applied to a subject, the more likely it is to happen that if we collectively agree on a future that we would prefer, that we may be able to actually influence the outcome by our collective focus on that.
Mm-hmm. Yeah, there's been some interesting experiments in that direction. I think they're called the Maharishi experiment, something like that, where a group of meditators, a group of people tried to modify the crime rate in an urban area. And through their effects, they could get statistical significance from the crime rate going up or down based on their either trying to decrease the crime rate through their mental efforts or not doing that. And there was clear statistical, in the how the crime rate went up and down basis of what they did. Was good correlation. So those kinds of experiments have been done.
So we really do have a whole raft of practical applications still to explore using the premise of M.B.T as a model, and like I say, that these extend into health, possibly into ways of changing society without the need for violent revolt or bloody revolution, and certainly ways for people suffering from poor mental or emotional health to see a way clear of finding a way from where they are now to somewhere that they would prefer to be in their kind of emotional well-being.
Well, one thing I might say, if some of your people are still hanging on out there,
we still have plenty. It's only the most moderate of erosion due to the hour.
Okay. Well, one thing I would like, you said that there were some people basically were skeptical and were having some issues. That's good. People need to be skeptical, and I'd like to make that point. I don't have these talks and kind of do these interviews with the idea that I can get people to believe what I say. That's not the point at all. You should be skeptical. It's important to be skeptical, and don't accept anything that you don't have your own information to verify, because if it's not your experience, it's not your truth. And you cannot carry around somebody else's truth. So skepticism is important. If you're not open-minded, you never have an opportunity to learn anything, because if you're closed, that's it. You're closed. You're not going to learn. So the key is to be open-minded and to be skeptical. That's the only process that will get you to a better understanding. So it's not a problem when somebody says, well, this doesn't make any sense to me, and here's why. They should be thinking that way. If it doesn't make sense to them, then they need to look at it.
We haven't done our job.
Where's the problem?
Yes.
Okay, well, again, Bob, you've been a fabulous co-host, and again, an absolute star for bringing Tom to the airwaves for us all. It's just been an absolute delight. Tom, you are, I would love to adopt you as my father. you can be adopted as my spiritual father if you like. I never could have imagined being able to feel such a completeness with and comfort with the model that I now work with in order to describe my reality. And as an epileptic, that has led me into so many dark places in my life that would just have been completely unnecessary in the firm knowledge of your M.B.T. and its consequential.